There's a metal out there almost nobody ever sees. But it's what turns steel into armor. How is it that just a few grams of vanadium per ton can boost a structure's strength by tens of percent and literally lighten the weight of the world? Where does this element hide if it's almost never found pure in nature? And why is it often extracted not from ore, but from dark slag that others consider waste? Today, you'll witness vanadium's journey. Hellish furnaces, blinding molten metal, fire-colored powder, and the birth of ferrovanadium that transforms steel in an instant. And at the end, I'll reveal why control over vanadium is no longer just metallurgy, it's geopolitics. Vanadium holds a special place among industrial metals, though for most people it remains nearly invisible. It's rarely seen in pure form, it's not used for jewelry, and it's barely associated with everyday life. Yet vanadium became one of the key factors in the creation of armored steels and modern high-strength structures, without which bridges, skyscrapers, automobiles, and heavy machinery would be impossible to imagine. The history of vanadium as a metal begins in the 19th century, but it gained real industrial significance much later, when metallurgists understood how even tiny amounts of this element could radically transform steel's properties. In nature, vanadium almost never occurs in its free state. Most of the time, it's found in complex minerals and ores, particularly vanadium-bearing titanomagnetites, and also in magnetite, where it replaces some of the iron atoms in the crystal lattice. The major vanadium ore deposits are concentrated in China, South Africa, Russia, and a few other countries. Mining is typically done through open pit or underground methods, depending on how deep the ore bodies lie. Magnetite ore with vanadium impurities goes through crushing and enrichment after extraction, where they separate out a concentrate with high iron and vanadium content. At this stage, the material isn't split into individual metals yet. It's a complex mixture of oxides. Vanadium's next stop, where metallurgy becomes a true industrial spectacle. Melting magnetite concentrate happens in blast furnaces or electric arc furnaces running at temperatures over 2700 degrees Fahrenheit. Inside the furnace, a mass of ore, coke, and fluxes slowly descends, passing through zones of different heat where solid chunks first sinter together, then transition into liquid. Molten iron collects at the bottom of the furnace, while lighter components, including vanadium oxides, concentrate in the upper slag layer. When the moment of release arrives, the furnace opens, and glowing streams pour out. Liquid slag glows with a blinding yellow-orange light, flows through channels, and throws up clouds of steam when it hits air or cooling surfaces. Right there in that seemingly spent mass lies the core treasure for vanadium production. After cooling, the slag transforms into solid, brittle chunks of dark material, deliberately collected and hauled away for further processing. Next up, crushing. Big pieces of slag pass through crushers and mills, getting ground into granular material or powder. The process hums with machinery, vibrations, and clouds of fine dust, immediately sucked away by filtration systems. The pulverized slag is prepped for chemical treatment, where vanadium needs to be extracted from an incredibly stable oxide matrix. Then the material enters reaction tanks filled with aqueous solutions of alkalis or salts. Under controlled temperature and constant stirring, leaching takes place. Vanadium compounds gradually transition into solution, shifting its color from pale yellow to rich orange or reddish. These visual changes directly indicate metal concentration and allow operators to monitor the process in real time. The resulting solution undergoes several purification stages. It's filtered, removing insoluble impurities, followed by precipitation, adding reagents that selectively bind vanadium. Inside the reaction vessels, a fine precipitate appears, gradually compacting and separating from the liquid. After washing and drying, this material becomes vanadium pentoxide, a bright powdery substance with a distinctive yellow-orange hue. From this moment on, vanadium stops being a hidden component in slag and becomes an independent industrial raw material. Vanadium pentoxide is then used to produce ferrovanadium, or is reduced to its metallic state. This entire sequence, from blinding molten metal to fine powder, vividly demonstrates how, deep within metallurgical processes, a material is born that defines the strength and reliability of modern steel. China produces 70,000 tons of vanadium annually, far exceeding the output of other countries and making it the global leader in both production and consumption of this metal. In terms of consumption, 90% of all vanadium goes into metallurgy, especially into high-strength microalloyed steels, where small additions of vanadium significantly increase mechanical strength, impact toughness, and fatigue resistance of structures. Ferrovanadium production is the critical link between chemical vanadium enrichment and the steel industry. It's in this alloy form that vanadium is most conveniently introduced into steel, precisely dosing its content and ensuring uniform distribution throughout the melt. The primary raw material for the process is vanadium pentoxide, obtained after processing slags or ores, along with metallic iron or iron-containing alloys. The process begins with charge preparation. Vanadium pentoxide is mixed with reducing agents, typically aluminum or silicon, and iron in strictly defined proportions. Next, the mixture is loaded into crucibles or electric furnaces, where conditions are created to reduce vanadium from its oxide state. Temperatures in the reaction zone reach over 3,600 degrees Fahrenheit, and it's at this moment that one of the most intense stages in the entire production line occurs. During aluminothermic or silicothermic reduction, the reaction proceeds extremely rapidly and releases a significant amount of heat. Vanadium oxides surrender their oxygen to the reducing agent, while pure vanadium transitions into a molten state and immediately dissolves in the iron. The result is liquid ferrovanadium with a specified metal content, typically ranging from 40 to 80% vanadium, depending on customer requirements. After the reaction completes, the melt is held to stabilize its composition, then poured into molds. As it cools, the ferrovanadium crystallizes, forming solid ingots or granules with a characteristic dark gray surface. The material is then crushed to a convenient size, packaged, and shipped to steel mills. The main value of ferrovanadium lies in its predictable behavior in molten steel. It dissolves quickly, is barely lost during melting, and allows precise control over microalloying. That's exactly why ferrovanadium became the standard form of vanadium supply for producing high-strength steels, from building structures to automotive components and armored products. The key feature of vanadium is that it works in microdoses. To get a noticeable effect, just tenths or even hundredths of a percent are enough. This means that for 1 ton of steel, only grams of vanadium are used, but those grams can boost yield strength, toughness, and durability by tens of percent. At the scale of millions of tons of steel, this delivers massive savings in metal, energy, and transportation costs. That's exactly why vanadium is often called the metal that lightens the weight of the world. Few people realize that vanadium also plays a role in long-term durability. Its compounds slow down grain growth at high temperatures and under repeated loading. This means structures made with vanadium steels age more slowly, handle cyclic loads better, and withstand sudden temperature swings. In real-world conditions, that translates to years of extra service life without repairs. Vanadium has become a critically important metal for infrastructure, and many countries have added it to their strategic materials lists. Control over vanadium flows means control over steel quality, and therefore over construction, transportation, and defense capabilities. This factor is increasingly shaping the geopolitics of metals. Right now, beneath our feet, millions of dollars in platinum, through which liquid stone flows at 2,000 degrees. This is a factory where sand transforms into fiber thinner than a human hair, and somehow comes out stronger than steel. Most people think the most valuable thing here is the giant furnace, but they're wrong. The most expensive part is the invisible chemistry, without which the entire material literally crumbles to dust in seconds. Every factory guards this recipe like a military secret. Without it, there'd be no modern yachts, no wind turbines, no airplane fuselages. Today, we're going where outsiders aren't allowed. And the strangest part, we're saving for the end. The whole process starts with a pile of sand and rocks. They use pure silica sand, limestone, and kaolin clay. We're talking massive volumes. Every single hour, they dump tens of thousands of pounds of this mixture into the furnace. For anyone searching for fiberglass manufacturing technology, understand this. It's not just melted glass. It's a strict chemical formula where every percentage point of borates or calcium determines whether your future boat falls apart in the middle of the ocean. These ingredients get mixed in giant hoppers and fed into the furnace, where absolute fiery chaos reigns. The temperature inside that furnace hits 2,500 degrees Fahrenheit. It's so hot that if you threw a chunk of scrap steel in there, it would vanish faster than you could blink. The glass becomes liquid like water and starts glowing with a blinding orange light. Right now, we're standing next to the main source of danger. This furnace runs non-stop for years. The furnace walls are made of special refractory brick that slowly dissolves into the molten glass. Imagine living in a house that you're slowly eating yourself. After 3 or 4 years, they have to rebuild the entire furnace, and that costs a fortune. But the real magic of this plant is hidden below. Underneath the furnace, they've installed plates called bushings. These are the most expensive pieces of hardware you'll ever see in any industry. Each plate is made from an alloy of platinum and rhodium. Why not steel? Because any other metal would simply dissolve in the hot glass or oxidize within hours. A single one of these parts can cost more than $200,000. The plant has hundreds of them. That means right beneath us, there are millions of dollars worth of precious metals with molten rock flowing through them. Each platinum plate has thousands of microscopic holes. When the liquid glass passes through them under pressure, it comes out in thin streams. And this is where the coolest stage begins, the pull. These streams don't just fall down. They're caught by a winding machine spinning at over 60 miles per hour. The glass is pulled so fast, it becomes 10 times thinner than a human hair before it even has time to cool. If you search online for how fiberglass is made, you've seen these shiny threads, but feeling their speed in real life, that's a whole different story. Here's a huge problem right at this stage. Thin glass is an incredibly brittle material. If these strands just touched each other, they'd instantly grind apart and turn into dust. So while the strand flies from the bushing to the spool, it needs to be lubricated. Every fiber gets coated with a special chemical solution. This is each factory's secret weapon. This solution protects the glass from self-destruction and lets it bond with epoxy resin later. Without this chemistry, fiberglass would just be a pile of useless glass garbage. Now we're watching thousands of strands gather into one thick yarn called roving. A single spool like this can weigh 40 pounds and hold tens of miles of continuous strand. Look at these rows of machines. They run around the clock, creating material for wind turbine blades, yacht hulls, and aircraft parts. The scale of production here is mind-blowing. In a single day, this factory churns out enough fiber to wrap around Earth's equator several times. A lot of people ask why fiberglass is so strong. The secret? Glass in fiber form has no micro cracks like regular window glass does. It's pure molecular strength. Take a bundle of this fiber 1 inch thick, and you could lift a truck with it. But working with this stuff is a serious challenge. Glass dust is constantly floating in the air. Walk in here without protective gear, and within 5 minutes, your body starts itching like you fell into a patch of stinging nettles the size of a house. The workers here are used to it, but for a newcomer, it's a real test of endurance. Once the spools are wound, they're shipped to massive drying ovens. That's where the threads fully harden and the chemical protection bonds to the surface. Temperature inside those dryers? 280 degrees Fahrenheit. It's a long haul, 12 to 24 hours. If moisture gets trapped inside a spool, all bets are off. Mold, total loss of strength, you name it. For anyone interested in fiberglass construction, here's what matters. This material doesn't rot, doesn't rust. That's why shipbuilders love it. When you see enormous sheets of fiberglass cloth laid into molds for future vessels, You get why this factory matters. Without these thin threads, we'd still be building heavy, clunky structures out of metal that's terrified of every drop of salt water. The production cycle at this facility is a continuous flow of energy and materials. Every minute the furnace runs costs hundreds of dollars in gas alone. Now add the cost of maintaining platinum bushings and the salaries of specialists who know how to tame molten rock. This is an extremely high-stakes business. Any mistake in the glass formula will cause the strand to start breaking. If a break happens at 60 miles per hour, it creates a massive tangle of filaments that has to be cleaned up by hand, shutting down the entire line. Right now, we're passing the shop where fiberglass is chopped into small pieces 1 or 2 inches long. This chopped fiber is added to plastic to make it stronger. It's used to make parts for your cars, appliance housings, and even smartphones. When you're holding a tough plastic object, chances are there are thousands of tiny glass skeletons hiding inside it, made right here. At the end of our tour, we see the finished goods warehouse. Thousands of pallets stacked with gleaming white spools. They look absolutely peaceful, but inside each one lies the energy of a blazing furnace and the precision of precious metals. This production isn't just industry, it's the triumph of human ingenuity over raw matter. Turning sand into fabric that can withstand ocean pressure or open sea wind. That's what makes me marvel at these plants every single time. If you Google fiberglass applications in industry or fiberglass properties, you'll find thousands of pages of text, but nothing replaces that smell of hot glass and the feeling of static electricity coursing through your entire body on this factory floor. This is where the future of our infrastructure is born. I'm thrilled we got to peek inside this closed-off world. Fiberglass manufacturing remains one of the most secretive industries because every plant guards its own glass recipes and chemical coating formulas. It's a world of big money, extreme temperatures, and massive risks. But it's thanks to this insane process that we have lightweight cars, fast planes, and reliable buildings. I hope you enjoyed this walk through fire and platinum. We saw stone become spider silk and learned why it's so brutally difficult. Make sure to check out my other industrial deep dives where we break down the most fascinating factories on the planet. It was lively, it was scorching, and it was incredibly eye-opening. Thanks for taking this journey with me. See you on the next tour, where we'll find something else massive, complex, and absolutely one of a kind. Stay safe and keep away from molten glass unless you've got yourself a shiny silver heat suit. Worth mentioning here, a lot of people are curious about fiberglass for insulation or making composite materials, and this plant is the very first link in that entire chain. Every composite starts right here, at the platinum bushing beneath that blazing furnace. Without this foundation, there'd be no space rockets, no modern construction. See you in future videos, where we'll unlock the secrets of other off-limits facilities. Every year, humanity produces over 360 million tons of plastic. Most of it doesn't disappear. It decomposes over hundreds of years. But what if instead of oil, we could make plastic from sugar? In the very heart of Thailand grows a crop that can change this. Sugarcane isn't just a plant, but a solar biofactory that transforms light into the material of the future. From its sweet juice is born polylactide, a bioplastic that decomposes naturally. How do they create eco-friendly packaging from simple cane that could save the planet? Watch till the end, and you'll discover the secret the industry has been keeping quiet about. Sugarcane is a true biofabricator of solar energy. It belongs to the grass family and is grown mainly in warm, humid regions, such as Thailand, Brazil, or India. In Thailand, particularly in Chiang Mai, cane occupies thousands of hectares and is a key crop for the agricultural economy. Cane isn't grown from seed. It's propagated through cuttings, pieces of stems that have nodes with buds. They're planted in prepared soil, usually in furrows, at a depth of 2 to 4 inches. After a few days, the buds sprout and new shoots begin to form. This plant is very light-loving, so plantations are located in open areas. It needs lots of water, but doesn't like stagnation. so irrigation must be moderate and regular. Over 10 to 14 months, the cane grows to 7 to 14 feet tall. Its stems are thick, juicy, filled with sweet juice. It's in this juice that sucrose is contained, the basis for sugar production. During growth, the cane actively absorbs carbon from the atmosphere, converting it into organic substances. This makes it not only a source of energy, but also a natural absorber of greenhouse gases. Sugarcane is harvested when it reaches maximum sucrose concentration, usually 10 to 14 months after planting. In Thailand, the harvest season falls during the dry period, from December through March, when the plant is no longer growing, but accumulating sweet juice. In many regions of Thailand, manual harvesting is still used. It's hard work performed by experienced workers with machetes. Before this, the plantation is often burned to remove leaves and ease access to the stems. Although this simplifies the process, burning harms the environment, so more and more farmers are switching to green cane. Harvest without fire. Large farms use mechanized combines that cut, clean, and chop the cane right in the field. This is faster, more efficient, and more ecological, though it requires investment. Important: cane residues, bagasse, aren't thrown away. They're used as biofuel, fertilizer, or even for making paper. This is an example of circular economy where nothing is wasted. After harvest, the cane must reach processing as quickly as possible. Otherwise, the sucrose level in the stems begins to drop, and that means quality loss. So logistics here is critically important. Trucks are the most common option in Thailand. Special open platforms or beds with high sides allow transporting large volumes of cane. Buggies or tractors with trailers are often used for short distances, from field to loading point. In some regions where there's appropriate infrastructure, cane is transported by rail cars. This is efficient for large volumes and long distances, but less flexible than motor transport. Water transport is a rare but possible option in areas with canals or rivers. It's used mainly for export or movement between regions. Cane is often not chopped in the field, but transported in whole stems. They're laid horizontally, densely, to minimize losses. At the factory, chopping, pressing, and juice extraction already occur. Large agricultural enterprises use automated loading systems that speed up the process and reduce losses. In smaller ones, work is still done manually or with simple mechanisms. When trucks with sugarcane arrive at the factory, the technological process begins that transforms the green plant into an innovative material, polylactide. This is a complex but fascinating journey where agricultural biomass becomes part of the ecological future. Before the cane enters processing, it's checked for sucrose content. Samples are taken from each batch to determine how suitable it is for production. Then the stems are cleaned of leaves and foreign impurities, manually or mechanically. Then our cane needs to be chopped. For this, the stems pass through mechanical crushers. These are large rollers or rotary machines with sharp blades that cut the stems into small fragments. The goal is to maximally open the cellular structure to ease juice extraction. The chopped cane is pressed in special rollers. Under high pressure, sweet juice rich in sucrose flows out. This juice is collected in reservoirs. The juice undergoes filtration to remove impurities, and then is heated for concentration. Next, a process similar to brewing kvass or yogurt is launched. Special bacteria are added that transform sugar into lactic acid. It's like when microbes turn grape juice into wine. Only here it's not alcohol that comes out, but acid. This process is called fermentation. It occurs in large tanks, bioreactors. There, everything is controlled. Temperature, acidity, how many bacteria are there? So they work properly and don't slack off. Lactic acid is the key ingredient for creating bioplastic. It has properties that allow transforming it into a polymer. The lactic acid is purified and subjected to polymerization, a chemical process in which molecules connect into long chains. The result is polylactide, a thermoplastic polymer that looks like granules or threads. These granules or threads are the basis for producing packaging, tableware, textiles, 3D printing filaments, and other products. Polylactide has high transparency, strength, and heat resistance, making it an ideal substitute for traditional plastic. Polylactide granules are poured into special machines, extruders or thermopresses. There, they're heated to the required temperature until they become a viscous mass. The hot mass is passed through forms or dies. For packaging and bags, the extrusion method is used, that is, pulling hot polymer into long ribbons or film. Cups, containers, spoons, and so on are made by filling corresponding forms with polymer under pressure. To create more complex shapes, like coffee lids, heated film is pressed to the form with a press. As soon as the product is formed, it's quickly cooled, with water, air, or special cooling plates. This is needed so the material hardens and doesn't deform. Finished products are trimmed, polished if needed, checked for quality, and packed for delivery. Before packing, each product undergoes visual inspection or automatic checking for defects, cracks, deformations, irregularities. In large productions, this is done by robotic systems with cameras and sensors. Defective products are often remelted, since polylactide allows reuse without quality loss. After final cooling, polylactide products, still warm from machine touch, set out on their last journey, to the packing line. Here, everything works smoothly. Mechanical arms carefully stack cups in perfect stacks, 50 in each. Product groups are wrapped in biodegradable film or cardboard boxes. Packaging can also be made of polylactide. That is, the product and its wrapper are made from the same material, which simplifies recycling. Afterward, labels are applied with information: polylactide type, production date, batch, disposal instructions. Finished boxes with products are stacked on pallets, wrapped with stretch film, which is often also bio, and sent to warehouses or to customers. Storage temperature is room temperature, but without excessive humidity, so polylactide doesn't start decomposing prematurely. Green packaging is no longer just fashion, but a demand of the times. Videos about plastic harm get millions of views, and brands are looking for alternatives that don't harm the environment. Polylactide from cane is one of the most promising options. After all, cane grows quickly, and the production process doesn't require crazy resources. Every single second, over 100 tons of new trash gets created around the world. Think about it. While you're watching this video, an entire truckload of waste appears on our planet. Where does it all end up? For years, the answer was simple: China. That's where Europe, America, and Japan shipped millions of tons of used bottles, paper, and scrap metal. But one day, China said, "That's enough." And suddenly, the world faced a garbage meltdown. But here's the mystery. Why would a country that banned importing other people's trash start searching for it just a few years later? Stick around till the end. You'll discover the secret that flipped the global recycling industry upside down. For many, many years, the entire world, especially wealthy countries in Europe, America, and Japan, got comfortable with a very convenient setup. They'd collect their trash, old plastic, paper, scrap metal, and simply ship it off to China. Massive container ships sailed across the oceans, loaded with tons of used soda bottles, old newspapers, and broken toys. China was like the world's global trash can. But not just a can. It was also a massive recycling operation. Chinese factories would take this waste, sort it, process it, and turn it into new products that they'd sell right back around the world. It was incredibly profitable for China. They got cheap raw materials and created jobs. And for other countries, it was perfect. They got rid of their garbage problem for relatively little money. Everybody was happy, right? Well, almost. But then, around 2018, China said, "Enough." Imagine a huge meeting of Chinese officials where the decision rang out: "We're done accepting other people's trash." They called this policy, very characteristically, National Sword. It was like if your neighbor, whose garage you'd been dumping your junk in for years, suddenly said, "That's it, take it all back. My garage is full and I'm sick of this." And that's when real chaos erupted. Countries that had been carelessly shipping their waste to China for years suddenly found themselves with millions of tons of garbage with nowhere to go. Picture this. Warehouses across Europe and America started filling up with mountains of plastic and paper that were supposed to sail to China, but now had no destination. It was a genuine shock to their recycling industry. What were they supposed to do with all this trash? Dump it in the Pacific Ocean? Toss it in deserts like in post-apocalyptic movies? Of course not, but the panic was massive. Some countries started burning waste in incinerators, which isn't great for the environment since it pollutes the air. Others scrambled to find new trash cans in Southeast Asia, Vietnam, Malaysia, Indonesia. But these countries quickly started pushing back too, because they didn't want to become the world's dumping grounds either. But here's where it gets really interesting. While the world frantically searched for somewhere to shove their plastic mountains, China started feeling a strange hunger. A hunger for plastic, a hunger for waste paper, a hunger for scrap metal. Seems impossible, right? A country that generates the most trash in the world suddenly experiencing a shortage of it? It's like a millionaire who suddenly went broke and is now searching for loose change under the couch cushions. The thing is, Chinese industry had gotten hooked on this imported high. Recycling plants, of which there were, to put it mildly, plenty in the Middle Kingdom, had gotten used to working with cheap, abundant, though not always quality, imported waste. Imagine a huge factory that processes tons of plastic bottles from Germany or the US every day. Its conveyor belts ran non-stop. Its workers knew their job. Its owners counted their profits. And suddenly, bam! The tap of imported raw materials got turned off. National Sword didn't just cut off imports. It left this entire massive industry without its usual food supply. Factories stood idle, capacity sat unused, and business owners pulled their hair out. But why couldn't they just switch to their own Chinese garbage? After all, there are billions of tons of it, right? That's where the devil's in the details. The problem isn't the absence of trash altogether, but the absence of quality, sorted, clean raw materials. The problem is that Chinese citizens don't know how to sort trash. Imagine this. People lived for decades, just like we used to, following the principle of everything in one bin, then off to the dump somewhere. That's the easiest way, you gotta admit. No need to think about anything. No need to separate anything. Just toss it and forget it. And this system that formed over generations, this habit that took root deeper than the oldest tree, suddenly turned out to be wrong. The Chinese government, facing these trash mountains growing faster than bamboo after rain, decided, yeah, this has to stop. We're starting to sort. But something went wrong. Sure, in big cities like Shanghai, where millions of people live in tight quarters, they started implementing mandatory waste separation. Imagine, now you don't just throw out trash, you have to divide it into 4, sometimes 5 different categories. Wet waste, dry waste, recyclable waste, and hazardous waste. And all this has to be thrown out at strictly defined times, in strictly defined containers. But that's just the tip of the iceberg. First, even what gets sorted often doesn't meet the cleanliness standards required for recycling. Imagine a plastic bottle you tossed in the right container, but it was poorly washed and still had yogurt residue inside. Or a pizza box soaked with grease. Things like this, if there are too many of them, can ruin an entire batch of raw materials, making it unsuitable for recycling. Recycling plants that previously worked with more or less standardized imported plastic that had already gone through initial sorting abroad suddenly faced Chinese reality, a mixture that requires additional, expensive cleaning stages, or simply gets rejected. Second, logistics. Collecting billions of tons of trash is one thing, but collecting it in such a way that it reaches recycling plants as clean, sorted raw materials that can be economically viable to recycle, that's a completely different story. In many areas of China, especially in smaller cities and rural areas, the secondary raw material collection system is still very primitive. There, trash is still collected haphazardly, and sorting often happens right at the dump site, by hand, which hardly guarantees high quality. But there's another interesting angle here. China is a country that's constantly trying to upgrade itself to become a leader in everything. And with trash recycling, it's the same story. After National Sword, they decided, okay, if we can't import, we'll build the world's best system ourselves. And they started building, modernizing, investing. New, modern, high-tech recycling plants appeared. They're equipped with the latest equipment, capable of processing massive volumes of secondary raw materials. But they need these raw materials. Clean, quality, preferably pre-sorted. And that's where the paradox emerges. There are plants, there's technology, there's the will to recycle, but there's not enough of the right trash. Picture a giant gleaming factory where robots work, but the conveyor belts move sluggishly because trucks haven't brought enough quality plastic. Or they brought it, but it's so contaminated that it has to be sent to the landfill instead of being recycled. It's like building a luxury restaurant with the best chefs, but having a shortage of fresh ingredients. This hunger for trash isn't just an economic problem, it's also a driver for further change. It's forcing China to accelerate reforms in waste management. The government is putting even more pressure on cities to improve their waste separation and sorting systems, educate the public, and implement fines for improper sorting. New logistics chains are being created for efficient collection and transportation of sorted secondary raw materials to recycling plants. Systems based on artificial intelligence and robotics are being developed for more accurate and efficient trash sorting. Imagine sorting robots analyzing every piece of plastic, determining its type and cleanliness. China aims not only to recycle, but also to use recycled materials in its own production, thereby closing the circular economy loop. This means that a system that previously relied on external sources of raw materials now has to completely reorient itself to internal, more finicky sources. And this trash hunger paradoxically pushes China to finally build a truly efficient and environmentally responsible waste management system. It's like a dragon that created a problem for itself just to heroically solve it later. And who knows, maybe in a few years, China will be not only the world's biggest trash producer, but also its biggest and most efficient recycler. That's the tangled but fascinating trash story from the Middle Kingdom. Every year, humanity produces over 4 billion tons of concrete, more than any other material on the planet. It's what our cities, bridges, and roads are built from. But every crack is like a tiny timer ticking toward destruction, started the moment water seeps inside. Now imagine concrete that actually lives, breathes, and heals itself. No people, no repairs. Deep in labs across the Netherlands, USA, and Japan, a game-changing material is being born. Inside it, bacteria or microcapsules that can seal cracks on their own, just like skin healing after a wound. How is this even possible? How did a lifeless material gain the ability to regenerate? Stick around until the end, and you'll find out how scientists brought concrete to life. Self-healing concrete. Sounds like something out of a sci-fi movie, but it's already here. Scientists invented it to solve one of construction's biggest headaches: cracks. Regular concrete starts drying out and cracking over time from temperature swings, moisture, or just plain stress. And a crack isn't just a scratch. Water gets inside, the rebar starts rusting, the structure weakens, and eventually, you're looking at expensive repairs or even a collapse. That's why researchers decided to create concrete that can patch itself up, no human help required. Sounds crazy, but it's actually pretty logical. There are two main technologies that make this possible: microbiological and mineral. The first one uses real living organisms. So-called bioconcrete was developed by Dutch researchers, and the principle is pretty straightforward. They add special bacteria to regular concrete mix, usually Bacillus pseudofermis or Bacillus conii. These bacteria can stay dormant for years, like seeds in dry soil. Along with the bacteria, they add nutrients, usually calcium lactate. And while the concrete stays intact, the bacteria just sleep. But when a crack forms and moisture gets in, they wake up. That's when the real microscopic work begins. The bacteria start consuming the nutrient substrate and, through their life processes, produce calcium carbonate, basically the same mineral that makes up seashells and limestone. That's what seals the crack from the inside, like the concrete is fixing itself. The results are impressive. Micro cracks up to 0.03 of an inch can disappear completely within a few weeks. And all without human intervention, purely thanks to nature that's been built into an artificial material. The second technology is less alive, but no less impressive. Instead of bacteria, it uses chemistry. Tiny capsules are added to the concrete containing an active substance inside. For example, epoxy resin or sodium silicate. These grain-sized capsules are evenly distributed throughout the mix. When the concrete cracks, some of the capsules burst too. The substance inside comes out, fills the crack, and hardens on contact with air or moisture. The result is the material literally heals itself. It's similar to how certain car paints can heal scratches with heat, except this process is way more complex and large-scale. The advantage of this approach is that it works even in dry conditions, where bacteria might not activate. The downside is cost. Creating the capsules is more complex, so this concrete is pricier. But when you calculate the cost of repairing bridges or tunnels, it becomes clear. The payoff is huge. Interestingly, these technologies don't cancel each other out. Some companies are experimenting with combining biological and chemical methods to create concrete that could self-heal under any conditions. Underwater, in the desert, or in freezing cold. Testing shows that structures made with this concrete last 2 to 3 times longer than regular ones. Bridges, roads, dams, parking garages, all of this can be made nearly eternal. For example, the Netherlands already built a lakeside lifeguard station using bioconcrete, and after several years, it hasn't needed any repairs. The idea is spreading fast around the world. In the US, these materials are being tested in bridges, in the UK, in sidewalk paving, and in Japan, even in concrete for coastal reinforcements that have to withstand salt water. Regular concrete, even the highest quality, has a shelf life, roughly 50 years. After that, cracks start appearing, water penetrates inside, rebar rusts, and the structure gradually weakens. Self-healing concrete changes these rules. Thanks to bacteria or microcapsules, it can heal microdamage before it becomes a problem. That's why the service life of structures can nearly double, from 100 to 120 years. That means one bridge or building can stand for 2 human generations without major repairs. Sure, this material isn't cheap yet. It costs several times more than regular concrete, on average 3 to 5 times more. But if you look at the long game, it's totally worth it. Maintaining, repairing, and restoring structures costs governments and companies millions of dollars every year. Self-healing concrete cuts those costs to a minimum. Basically, it's like buying a car that changes its own oil and fixes its own brakes. Expensive upfront, but then smooth sailing and economical. The Netherlands became the real home of self-healing concrete. Right here, at Delft University of Technology, the idea emerged to add living bacteria to the mix that could repair concrete from the inside. The man behind this idea is Dutch microbiologist and engineer Hendrik Jonkers. Nature inspired him. He noticed that certain bacteria can survive in limestone rock and create mineral deposits, filling micro cracks in stone. That's when Jonkers asked himself, if nature can heal stone, why not make concrete that does the same? In the early 2000s, he started experiments with different bacterial strains, looking for ones that could withstand concrete's alkaline environment and stay viable for years. After numerous trials, the best candidates turned out to be Bacillus pseudofirmis and Bacillus conii, spores that can sleep for decades and activate only when moisture appears. Jonkers added them to concrete along with a food source, calcium lactate. The results were mind-blowing. When the concrete cracked, the bacteria woke up and produced calcium carbonate, which sealed the cracks like natural glue. Jonkers called his invention bioconcrete, and soon the whole world was talking about it. Later, Delft University launched a project to test bioconcrete under real-world conditions. In 2015, the Netherlands built the first lakeside structure using this material. Years later, it remained in excellent condition without any repairs. Now Jonkers' lab is working with construction companies and governments from other countries, perfecting the formula to make it cheaper and more accessible. The USA and UK bet on the mineral technology for self-healing concrete, which doesn't require living organisms, but works through special microcapsules with healing substances inside. These countries are actively investing in research on materials that can automatically restore minor damage without human involvement. The principle is pretty simple, but looks impressive. Capsules or microcapsules filled with special gel, epoxy resin, or sodium silicate are added to the concrete mix. When the concrete surface stays intact, the capsules preserve their contents without reacting with the environment. But as soon as a crack appears, the capsule ruptures and the liquid flows into the damaged zone. On contact with moisture or oxygen, the substance hardens, gluing the crack edges together and returning the structure's original strength. These systems are currently being tested in US Army labs and British research centers, including Cambridge University. In the UK, they're even building experimental road and bridge sections with this material to track how it behaves under rain, vibrations, and temperature swings. American experts went even further. They're experimenting with capsules that can activate multiple times. Inside these capsules are microgels that not only fill cracks, but also expand on contact with water, creating a hermetic barrier against corrosion. This is especially crucial for bridges and skyscrapers in coastal cities, where concrete constantly faces moisture and salts. Test results show that cracks up to a few hundredths of an inch wide can seal themselves in less than a week. And if the damage is larger, the process takes longer, but still happens without human involvement. Such technologies can significantly extend the service life of roads, tunnels, and even military structures, which is especially valuable under extreme loads. Thousands of planes, just sitting in the desert. They'll never fly again. But each one, millions of dollars being carefully stripped away, bolt by bolt, right now. One engine, 30 million. Business class seats, a few thousand each. Even the coffee maker from an old Boeing gets auctioned off. People think aircraft boneyards are graveyards. But the truth is, they're the most profitable recycling operations on the planet. Today, we're going where almost no one gets to go. To watch a 150-ton giant get torn down to scrap metal in 30 minutes. And why this isn't the end at all. It's a whole new beginning. Why the desert? That's the first question that pops up when you see these thousands of acres packed with plains. It's pushing 100 degrees Fahrenheit out here, and the humidity's basically zero. Perfect conditions to keep metal from rotting and rusting. Planes can sit here for decades and still look like they rolled off the tarmac at JFK yesterday. But not all of them are here to die. A lot are just waiting for better times. The airplane recycling process starts with what the pros call harvesting. This is the most profitable part of the job. When an airline decides a plane is no longer flight-worthy, engines are the first things to go. One of those engines can run anywhere from $10 to $30 million in working condition. They're pulled using special lifts and shipped off for diagnostics. Even if the airframe itself is old, those engines can keep flying on other aircraft for years to come. It's like a heart that keeps beating in another body. Besides the engines, they remove the auxiliary power unit. That's a small engine in the tail of the plane that provides electricity when the main motors are shut down. That thing's worth serious money too. Next, we step inside the cockpit. For aviation fans, this is like Aladdin's cave. There are hundreds of switches, screens, and computers. Each black box or navigation instrument can fetch several thousand or even tens of thousands of dollars on the secondary market. Workers remove all the equipment very carefully, pack it into special anti-static boxes, and send it for testing. Same goes for the passenger cabin. You'd be surprised, but even the seats have value. A set of business class seats can be sold for several $1,000s to private companies or movie studios building sets. Galleys, meal carts, even coffee makers, everything goes up for sale. There's nothing worthless on a plane until it's just an empty metal tube. Once everything valuable is stripped out, the environmental specialists step in. An aircraft is a complex machine packed with hazardous fluids. Every last drop has to be drained. The fuel tanks of a large plane can still hold several hundred gallons of kerosene that can't be pumped out during normal operations. Hydraulic fluid also needs draining. It's highly toxic, along with lubricant from all the mechanisms and antifreeze. Just imagine, the total volume of all these technical fluids can reach 500 gallons. All of it gets drained into special tanks for proper disposal. Workers also remove batteries, fire extinguishers, and oxygen cylinders. If even one of those cylinders stays inside when the heavy machinery moves in, it can explode with the force of an artillery shell. When the plane becomes completely clean, the most spectacular part begins, destroying the fuselage. Here we see a giant excavator at work, but instead of a bucket, it's equipped with hydraulic shears. They're sometimes called the guillotine. The operator of this machine is a true master. He drives up to the aircraft and starts chomping off pieces of the wings. The sound is like someone tearing open a giant soda can, only 1,000,000 times louder. The metal crunches, cracks, and gives way under pressure of several thousand pounds per square inch. First they cut off the wings, then the tail section. All of this is done according to a specific plan, so the structure doesn't collapse onto the machine itself. Next, the excavator tackles the fuselage. It simply slices this massive steel tube into chunks about 20 feet long. This is done so these pieces can be loaded onto regular trucks and hauled to the metal mill. Watching what was once a majestic airliner that flew at 30,000 feet get turned into a heap of mangled metal in 30 minutes. It's a sight that makes you think about how fleeting time really is. But the equipment operators don't have time for philosophy. They need to sort the scrap as fast as possible. Sorting is the key to profit in this business. An aircraft is made up of different metals, and they can't be mixed. About 80% of the weight is aluminum, but it also comes in different grades. The skin is one alloy. The structural beams inside are another. There's also titanium, which is used in high temperature areas, like near the engines. Titanium costs several times more than aluminum, so there's a real hunt for every piece of this metal. There's also steel in the landing gear, and some copper in those leftover wires that couldn't be pulled out by hand. Workers use magnets and special scanners to separate these piles of metal. A lot of people think aircraft scrap is the end of the story, but it's actually the beginning. The aluminum from these planes, it's the highest quality metal. They melt it down at around 1200 degrees Fahrenheit and make new ingots. From that aluminum, they can then make just about anything. Beer cans, parts for new cars, or even new aircraft. It's a closed loop where nothing goes to waste. Experts say roughly 95% of a modern passenger jet's weight can be recycled and used again. That's an incredible number for such complex machinery. Here's a fun fact for those who love numbers. In 1 year at a boneyard like this, they can completely dismantle up to 200 aircraft. If you take the average weight of each at 150,000 pounds, that's 30 million pounds of metal going back into the economy. This is a billion-dollar business, and it's only growing because airlines are trying to upgrade their fleets faster to more fuel-efficient models. Older planes become too expensive to maintain, so they end up right here, under the Arizona sun. There's always something a little sad about watching planes die, but at the same time, I'm blown away by how incredibly organized this whole process is. There's no chaos here. Every swing of the excavator, every step a worker takes with a wrench in hand, it's all calculated down to the second. This is a massive machine that converts the past into the future. We've just watched hydraulic power transform a symbol of technological progress into raw material for new achievements. And even though these aircraft will never take to the skies again, they live on in the things we use every day. As we walk across this yard, there's a constant crunch of broken glass and insulation debris under our feet. The air smells like hot metal and dry grass. It's a unique atmosphere that's tough to capture in words. This is where engineering genius meets inevitable destruction. But it's not destruction for destruction's sake. It's destruction for the sake of creating something new. And that's really what our civilization is all about. We're constantly recycling the old to build something better, faster, and more efficient. I hope you enjoyed peeking behind the fence of this aircraft graveyard with me. Now, next time you're flying off on vacation, you'll know what awaits your plane in 20 or 30 years. And it's not scary at all. It's just another chapter in the life of metal and technology. Thanks for watching my explorations. Hit that like button if you're into massive machinery like this, and subscribe so you don't miss new journeys to the most fascinating places on our planet. We'll find plenty more spots where metal tells us its incredible stories. See you in the next video, where we'll tear apart something just as epic. Bye. Today, I dragged you to a place so remote that cell service seems like technology from the distant future. And the main bosses here are massive excavators with wheels big enough to comfortably fit a small studio apartment. We're starting our journey at a nickel mine. Have you ever wondered where that perfect shine on a surgeon's scalpel comes from? Or why your pot doesn't turn into a pile of rust after cooking your first batch of borscht? The answer lies here, 1,600 feet beneath our feet. Nickel. This is the guy that makes steel tough and resistant to just about everything. But finding it? That's an adventure for the patient. Look at these numbers. To extract just 1 ton of pure nickel, miners have to move and haul to the surface about 100 tons of ore. That means the useful metal content in this rock ranges from 1 to 3%. Massive underground machines load up rock that looks like ordinary gray stone, but hidden inside is the promise of future strength. One of these dump trucks carries 240 tons of rock at a time. That's the weight of roughly 40 adult elephants, if you like those kinds of comparisons. After we've brought the ore to the surface, it's got a long journey ahead to the processing plant. There, the stone gets crushed into fine sand, washed, sifted, and turned into concentrate. It's not metal yet, but it's getting close. Then this concentrate gets shipped to a metallurgical plant. And this is where things get really interesting. And really hot. We're standing inside a shop where electric arc furnaces are doing their thing. Here, temperatures climb to 3,000 degrees Fahrenheit. That's roughly 10 times hotter than your home oven when you're trying to roast that holiday duck. All this molten metal churns like fiery soup, glowing so bright that without special goggles, you really shouldn't look at it. Not if you plan on seeing anything else for the rest of your life. Into the furnace goes scrap iron, that same nickel, and one more critical player, chromium. Chromium is a whole story unto itself. For steel to officially earn the right to be called stainless, it needs at least 10.5% chromium. When this metal contacts oxygen, it forms an invisible, incredibly thin oxide film on the surface. It's so thin we can't even see it, but it becomes that impenetrable barrier that keeps the iron from oxidizing. So stainless steel doesn't rust, not because it's magical, but because it's already coated with a protective layer at the atomic level. Once the steel melts, it goes through a procedure called argon-oxygen decarburization. Sounds like the title of a PhD thesis, but the idea is pretty straightforward. Surgical steel has to be incredibly pure and contain extremely little carbon. Too much carbon? It'll buddy up with the chromium, steal it away, and the steel loses its resistance to corrosion. A mixture of gases is blown through the molten metal under immense pressure, literally burning out the excess carbon while leaving all the useful additives in place. The whole process takes about 90 minutes. You can't rush this. One mistake in the proportions, and instead of a valuable medical instrument, you get ordinary rebar that'll be covered in rust spots within a few months. Next, this fiery liquid gets poured into continuous casting machines. Steel solidifies into long, massive strips that professionals call slabs. A single slab can weigh 20 tons and stretch about 40 feet long. When they come out of the machine, they're still glowing dark red, radiating so much heat you could toast bread in a fraction of a second without even getting close. Then these slabs head to the rolling mill. Picture a giant version of a rolling pin, except instead of dough, you've got a 20-ton chunk of red-hot steel, and instead of a baker's hands, you've got massive rollers pressing down on the metal with thousands of tons of force. The metal gets run through these rollers again and again, getting thinner and longer each time. From a slab 8 inches thick, steel workers produce coils of steel ribbon just a few hundredths of an inch thick. The speed at which steel flies through these rollers in the final stages hits 40 feet per second. It looks like an actual fiery arrow racing through the plant. Now let's jump to a completely different place. Gone is the hellish heat and roar. We're at a medical instrument factory. The atmosphere here feels more like an operating room or lab, sterile, quiet, and fanatically detail-oriented. That steel ribbon we saw earlier, it's cut into small blanks. Then each blank is heated again, but now in small induction furnaces and forged in special dies. That's how the rough profile of a future clamp, forceps, or scalpel emerges. After forging, the real precision work begins. Craftsmen use grinding machines and hand finishing to perfect every curve. This is absolutely critical, because a surgical instrument must be perfectly smooth. Not a single burr or microscopic pit where bacteria could hide and multiply. The tolerances here are so tight they're measured in microns. A human hair is about 50 microns thick. We're talking about precision down to 5 or 10 microns. Once the instrument takes its final shape, it goes through heat treatment. It's heated to 2000 degrees, then rapidly cooled. This makes the steel hard, so the scalpel won't dull after the first cut, and the clamp won't bend in the doctor's hands. But after hardening, the metal becomes brittle, so it's heated again slightly, a process called tempering, to restore the necessary flexibility. One of my favorite stages is passivation. This is when the finished, already shiny instruments are immersed in baths of strong nitric acid solution. You'd think, why torture a finished product? But the acid does something really useful. It dissolves any microscopic particles of regular iron that might have gotten on the surface from the machines or the craftsman's tools. This cleaning allows that same protective chromium film we talked about at the beginning to become even thicker and stronger. After this treatment, the instrument can handle thousands of sterilization cycles in autoclaves at 273 degrees Fahrenheit under 2 atmospheres of pressure and stay shiny and clean for years. Let's crunch some numbers here, because they always help us grasp the scale of what's happening. The world produces about 50 million tons of stainless steel every year. If you stretch that metal into a thin wire, you could wrap our entire planet thousands of times. But only a tiny fraction of that steel, less than 1%, gets to become a surgical instrument. To manufacture one quality operating room set, you've got to process hundreds of tons of rock, burn through thousands of kilowatt hours of electricity, and run over 30 different quality tests. For instance, one ordinary surgical clamp passes through the hands of at least 12 different specialists, from the blacksmith to the quality controller, before it lands in its packaging. Quality control here is so strict that a tool gets scrapped even for a microscopic scratch on the surface, something the naked eye wouldn't even notice without serious magnification. And here we see the final result, a tool weighing less than 2 ounces, but packed with the labor of thousands of people, from those who descended into dark mines for nickel, to those who calibrated the lasers for marking finished products. It's a long journey, where every step is a battle for quality and purity. Subscribe to the channel so you don't miss our next deep dives, because the world of manufacturing is way more fascinating than it seems at first glance. Thanks for watching, take care of yourselves, and choose only reliable tools for your life. See you in the next video. By the way, what do you think? Will humanity ever find a metal even stronger than today's steel alloys? Or have we already hit the peak of what's possible in this field? So, I know North Carolina doesn't sound particularly exotic, but what's being made here flies at 66,000 feet above the Pacific Ocean and keeps 400 passengers in the air at the same time. This is the factory that produces blades for the GE9X turbine engine series, the largest commercial jet engines in the world today. One of these engines weighs about 9 tons, generates thrust up to 105,000 pounds. Sorry, that's roughly 460 kilonewtons, and costs around $50 million. But we're not here because of the engine. We're here because of one specific part that's about the size of your palm and costs more than a nice car. A turbine blade. In the hot section of the engine, in what's called the high-pressure turbine, there are between 160 and 180 of them per wheel, depending on the stage. Each one weighs roughly 10.5 to 14 ounces. But the conditions it operates in, this isn't engineering anymore. It's straight up torture for common sense. The temperature of the gases flowing around the blade during engine operation, 2700 to 2900 degrees Fahrenheit. That's higher than the melting point of steel, higher than the melting point of the very material the blade is made from. How it doesn't just melt, I'll tell you in a minute, because it's one of the coolest things I saw at this facility. The blade material is a nickel-based superalloy. The exact recipe is classified, and they didn't tell me the full breakdown, which is fair. But the general principle is known. Each element is responsible for something specific. Take rhenium, for instance. It provides heat resistance and slows down creep. That's when metal under prolonged stress and temperature deforms completely. The raw material cost for a single blade runs from 200 to 300 euros just for the metal, before anyone's even touched it. Now, how it all begins. The blade manufacturing process is investment casting, also known in the industry as lost wax casting. First step, the wax model. An exact replica of the future blade, including all internal channels, is created from wax under pressure in a metal mold. The precision of this mold, plus or minus 20 micrometers. That's about a quarter of the thickness of a human hair. If the mold deviates any more than that, it goes back for refinement. But the wax model is just the outer form. Inside the blade, there are also cooling channels, thin, winding tunnels through which cold air from the compressor gets pumped during engine operation. That's why the blade doesn't melt, even though the surrounding gas is hotter than its own melting point. Inside, air at temperatures of 500 to 600 degrees Celsius flows through and keeps the metal in the working zone. These channels are formed separately, using ceramic cores that get inserted into the wax model before casting. The core looks like a thin, sturdy comb, and it occupies exactly the space where the channel will eventually be. The wall thickness between the blade's outer contour and the internal channel ranges from 1 to 2 millimeters. Any thinner, and the blade becomes brittle. Any thicker, and the cooling can't keep up. Next, the wax model gets dipped into a liquid ceramic slurry and coated with fine ceramic sand. Dip, pull out, dry, and repeat the cycle 8 to 12 times. Each layer dries for 4 to 8 hours. After the final layer, you get a ceramic blob about 10 millimeters thick, hard, rough to the touch, kind of like papier-mâché if papier-mâché were made from space shuttle material. Then this whole thing, with the wax still inside, goes into an autoclave, where at temperatures around 300 degrees Fahrenheit and elevated pressure, the wax melts out through a small opening. Hence the name, lost wax casting. What's left inside is a perfect negative of the blade shape. The ceramic holds its form, the cores stay in place. Now comes the metal pour. This is the part I came for. The molten metal gets heated to around 2500 to 2700 degrees Fahrenheit and poured into the ceramic mold. But they don't just pour it and wait for it to solidify. The mold gets slowly withdrawn from the heating chamber at a rate of about 1/10 to 1/5 of an inch per minute. That withdrawal speed controls how the metal crystallizes. If everything's done right, the entire blade, from root to tip, becomes a single crystal. Not a single grain boundary throughout the entire volume of metal. That's single crystal casting. Grain boundaries, the weakest spot in any metal. That's where cracks start under prolonged stress and heat. If there's only one grain, there's no boundary, no failure points. Heat resistance jumps roughly 30% compared to ordinary polycrystalline casting. After cooling, they break the ceramic shell, just mechanically, with hammers and vibration. Out comes a gray blade with ceramic cores inside. The cores come out in an alkaline solution at roughly 210 degrees. The chemistry dissolves ceramic, but leaves the metal untouched. This takes 4 to 8 hours. After washing, those same cooling channels remain in the center, clean, precise, completely open. Then they check the blade. X-rays reveal pores and cracks inside the metal. Fluorescent liquid catches surface defects. A special probe passes through each cooling channel, verifying it's not blocked by ceramic residue. If even one cooling channel is partially blocked, the blade goes straight to scrap. Not to rework, straight to scrap. Because you can't fix that. The rejection rate at this stage runs 2 to 5% per batch. Doesn't sound like much, but given what each part costs, we're talking real money. After inspection, heat treatment. The blade goes through multiple temperature cycles. First, around 1900 degrees for several hours, then a gradual cool down. This process evens out the internal stresses that formed during casting and locks in the alloy's microstructure. The exact heat treatment protocol? Also classified. When I asked, the manager who was walking me through just smiled and changed the subject. Final stage, protective coatings. First comes a metallic bond coat, nickel and aluminum based, applied using a plasma spray process. That's the foundation. On top of that goes the thermal barrier coating, zirconia stabilized with yttrium. It's ceramic. And it's that ceramic layer that absorbs the first several hundred degrees from the screaming hot gas stream. This layer is between 100 and 2 micrometers thick. The application looks like spray painting in a chamber. The blade rotates, the plasma gun moves along it following a preset path. But the temperature of the plasma stream during application is around 18,000 degrees Fahrenheit. For comparison, the surface of the sun is about 10,000 degrees. So the tool is nearly twice as hot as a star, but the blade itself doesn't heat up more than 4 degrees, because the entire process is incredibly fast and incredibly precisely controlled. The finished blade goes for final weighing, measurement, and registration. Each one gets an individual serial number and a passport where all parameters are recorded, from the chemical composition of the melt to the results of every control measurement. This document is kept for as long as the engine lives, and that's 20 to 30 years and tens of thousands of flight hours. On my way out, I asked how many blades they made per month. They told me it was in the range of several thousand units across all sizes. They wouldn't give me an exact number. But when you consider that one engine needs several hundred hot section blades alone, and orders for the 9X remain backed up for years ahead, you can imagine the scale. You're the best. Subscribe so you don't miss the next facility. It's going to be even more interesting. Write in the comments where you're from, and maybe next time I'll visit your city. In every second of our lives, there are metals we don't even suspect. Without them, there would be no smartphones, electric cars, or even jet aircraft. And now imagine a place where, in the middle of the desert, under the scorching California sun, the United States creates a strategic resource of the future, without a single pound of Chinese raw materials. Here, at Mountain Pass, they mine 43,000 tons of rare earth metals annually. Rocks that look ordinary are transformed into materials for lasers, engines, and defense systems. But there's something almost no one knows about. And if you watch till the end, you'll understand why this dust from the desert can change the world. Today here, in the dust and heat, MP Materials Company mines 43,000 tons of rare earth concentrate per year, all without a single pound of Chinese raw materials. For a country that for decades depended on imports from China, this is a strategic breakthrough. The main star of this place is bastnasite, a mineral that looks like an ordinary stone but contains treasures inside: lanthanum, cerium, neodymium, and praseodymium. These very elements give life to modern magnets, lasers, electric cars, and jet aircraft. Everything begins in the depths of the quarry. Huge excavators and 300-ton trucks carry rock to the crusher. Next comes the flotation process, similar to a magic sieve. Crushed ore is mixed with water and special reagents. All this turns into foam, and bastnasite particles float to the surface, while waste settles to the bottom. After flotation, bastnasite goes for chemical expertise. In MP Materials laboratories, it's transformed into concentrate, and then into individual elements. This is a complex sequence of extractions and washes, where each metal chooses its own path. Once, this stage was performed in China. Now the United States is gradually building a full production cycle, from ore to finished magnets. Thanks to this, the country has already replaced 80% of its former imports from Asia, and this is just the beginning. It sounds like science fiction, but it's a fact. 2 pounds of cerium can become material for optical lenses of laser systems in military equipment. Other elements, like neodymium, are used in powerful magnets of jet engines and in missile guidance systems. All this means that every ton of ore from Mountain Pass isn't just raw material. It's a piece of American defense independence. The California desert isn't just scorched by the sun. It's politically charged. Mountain Pass is a symbol of a new era where technology and geopolitics merge. Today, American engineers, in hard hats and safety glasses, are literally building their own supply chain of the future, step by step displacing the Chinese monopoly. Just as in the 60s, when the United States first launched a satellite, now they're trying to be first to build an independent rare earth elements industry. And it all starts right here, among the sands, where it was once quiet, but now machines rumble, and the fire of smelting furnaces glows. If you gather all the rare earth elements mined here per year, it's 43,000 tons of concentrate. Outwardly ordinary dust, but actually strategic raw material, more valuable than gold. And if this dust were transformed into finished products, it would power more than 100,000 electric vehicles, those that race without a drop of gasoline thanks to neodymium magnets in motors. The same metals would ensure the operation of hundreds of guidance systems for F-35 fighters, where precision depends on microscopic lasers and sensors. And also, tens of thousands of medical lasers used for eye surgeries or to stop bleeding in military hospitals. The irony is that Mountain Pass isn't a megapolis or a Silicon Valley laboratory, but a patch of land in the middle of the desert. But it's precisely this place that's becoming a PowerPoint again. Every kilogram of cerium mined here is a potential lens for lasers in defense systems. Every gram of neodymium is a piece of an engine for an electric car or satellite. It's worth talking separately about cerium. Cerium isn't just another metal on the list of rare earth elements. It's one of those that sits quietly beneath the surface of technologies, but without it, the modern world would look completely different. Imagine a desert quarry, drilling rigs, machine cries, and dust, and among all this, under sand and stone, hides a complex chemical actor that transforms from an ordinary mineral into a material that affects aircraft, phones, and even medicine. In appearance, an ordinary grayish powder, nothing special. But this is a true alchemist among metals. Without it, there would be no clean glass in telescopes, no shine in smartphones, no precision of lasers, and no cleaner air from automobile exhausts. 1 gram of cerium can do what other materials can't even in hundreds of times larger quantities. Cerium is a true master of transformations. In catalysts, it behaves like a chemical chameleon. It intercepts and releases oxygen, converting harmful gases into harmless ones. In glass, it extinguishes ultraviolet light, makes lenses transparent as crystal. Its oxide polishes phone screens, cameras, optical devices, literally erasing microscopic scratches from surfaces to perfect smoothness. Among workers at the plant, there's a joke. Without cerium, the world wouldn't shine. And there's truth in this. Because when it gets into engineers' hands, everything around starts to shine. Literally. It helps see farther, move faster, burn cleaner, heal more precisely. All this, from desert dust, from a place where heat reaches 110 degrees Fahrenheit, and wind sweeps away traces in a few minutes, as a symbol that even in the driest desert, the future can be born. Mountain Pass was once just a point on the map, the only mine of this type in all of North America. But now it's surrounded by an entire network of structures that transform crude ore into pure elements, ready for the most complex technologies, from electric motors to jet guidance systems. MP Materials Company has built here not just a mine, but a closed-cycle production, something America lost back in the 1990s when all supplies depended on China. After many years of research and investments in hundreds of millions of dollars, new lines operate almost without human participation. All processes are controlled by computers. Sensors measure compound purity, robotic cranes move containers, and special cameras capture every dust particle. Air in laboratories is so sterile that it feels like it's not a desert, but a space station. Everything that comes out of these shops is sent to other factories, which are also being built inside the country. In Texas and Ohio, they're building factories that will manufacture permanent magnets, precisely those that ensure the operation of Tesla electric motors, wind turbines, or fighter guidance systems. Once these magnets were supplied from China almost 100%, but now America plans to completely switch to its own materials by 2030. People who work here say they feel part of something bigger than just production. When they watch as a substance comes out of desert soil that will later turn into part of a satellite or a high-precision laser, it resembles a true miracle. Next to the quarry grow warehouses, laboratories, transport hubs, and on the horizon, also solar panels that power this giant. After the mine closed in 2002, when Chinese companies effectively monopolized the rare earth elements market, only a few dozen workers remained in the Mountain Pass area, maintaining security and basic infrastructure. The nearby settlement declined. Stores closed, roads overgrew with weeds, and local families moved out to look for work. When in 2017, MP Materials Company bought out the assets and launched a modernization program, the situation began to change literally from scratch. Over several years, more than 800 jobs were created at the enterprise itself, not counting hundreds of related ones, in transport, chemical supply, technical service, energy, and even local services. In neighboring towns, cafes reopened, schools received funding, and roads, repairs. Besides direct vacancies, MP Materials launched a professional training program, cooperating with local colleges. Graduates of technical specialties can now do internships right at the modern processing plant, where they learn to work with automated lines, flotators, hydrocyclones, and chemical separation systems. Interestingly, jobs here are very diverse, from geologists, chemical engineers, process operators, to programmers and data analysts who control plant operations through digital panels. Each shift means tens of thousands of parameters read by sensors in real time. In a broader sense, the revival of Mountain Pass has become a symbol of the return of American manufacturing, which for decades was exported abroad. Against the background of political statements about reshoring and strengthening the internal supply chain, this project is often cited as proof that even in the desert, you can create a modern, profitable, and stable industry. They extract it in mountains where stone is born from flames and pressure capable of crushing anything alive. Its formation takes hundreds of millions of years, and today, people cut it with diamonds at a speed of 20 miles per hour. But what if I told you that this shiny material, used to decorate palaces and statues, was once the bottom of an ancient ocean, and that every slab of marble is a frozen story of life, death, and time? Watch until the end, and you will see how nature creates its own masterpiece, and people try to uncover its secret. Marble is not just a beautiful stone for decoration or sculpture. It is a material that has millions of years of geological transformation behind it. Its journey begins deep underground, where temperature and pressure change ordinary rocks beyond recognition. The basis of most marble is limestone, a sedimentary rock formed mainly from calcite. Limestone is formed at the bottom of ancient seas and oceans from the remains of marine organisms, corals, mollusks, foraminifera. Over millions of years, these fragments settle, compact, and cement together under pressure to form thick layers. When such layers fall into a zone of tectonic processes, where the Earth's crust moves, compresses, or subsides, they sink into deeper layers of the Earth. There, the temperature can exceed 1,200 degrees Fahrenheit, and the pressure reaches 1,000 atmospheres. Under these conditions, metamorphism begins, the process of transforming rocks without complete melting, but with a change in their structure. During metamorphism, the calcite crystals in the limestone begin to recrystallize. The old grains disappear, and instead, new ones grow, larger, tightly fused together. This process gradually transforms the loose sedimentary rock into a solid monolith with a characteristic shine and granular texture. It is this structure that gives marble its famous ability to be polished. The variety of colors and patterns in marble is the result of impurities that got into the limestone during its formation or metamorphism. If there is iron in the rock, the marble acquires reddish or yellow hues. Graphite or organic matter makes it gray or black. Impurities of serpentinite or chlorite add green tones. Quartz, dolomite, and pyrite create veins, the same patterns that make marble seem alive. Marble is not formed instantly. The process can take hundreds of millions of years. In places where tectonic plates collide, for example, in the Himalayas, the Alps, or the Apennine Peninsula, the rocks experience the most intense pressure. That is why such areas have become world centers for marble quarrying. For example, Carrara in Italy, where white marble of extraordinary purity was formed. During metamorphism, degassing also occurs, the release of carbon dioxide that remained in the pores of the limestone. Because of this, the structure of marble becomes almost non-porous. This density makes it durable, but also more brittle with sudden changes in temperature. In some cases, the process of marble formation can be partially reversible. If the temperature is too high, the calcite begins to melt, forming intermediate forms between metamorphic and igneous rocks. Such transitional marbles are found in areas of contact between limestone and magmatic intrusions, for example, near granite massifs. Another interesting feature is the zonation of formation. In nature, it is rare for an entire layer of marble to have the same structure. In different areas, the pressure and temperature are different, so some layers are coarse-grained, others are fine-grained, some have veins, others have a uniform color. This explains why even within a single quarry, marble of a completely different appearance can be extracted. When geologists study deposits, they are looking for precisely those places where the limestone has undergone complete metamorphism, but has not been destroyed by excess heat or deformation. Sometimes these layers lie at a depth of several hundred feet. Sometimes they come right to the surface, as in Tuscany or Greece. The quarrying and processing of marble is no less fascinating a process than its formation. The modern marble industry combines powerful machinery, precise laser technologies, and artisanal craftsmanship that has barely changed since the time of Michelangelo. The first stage is the identification of the deposit. Geologists conduct research on mountain ranges using georadar, laser scanning, and drilling samples. The goal is to find a layer of marble of the required thickness, color, and uniformity. Sometimes the required layer lies almost on the surface, as in Carrara in Italy, or on the island of Paros in Greece. In other cases, it has to be uncovered, removing tens of feet of rock from above. When the site is prepared, the separation of marble blocks begins. Once, this was done with explosives, but now much more precise and safer methods are used. The main tool is diamond wire saws. This is a steel cable on which hundreds of diamond segments are strung. The cable is stretched between two pulleys and rotates at a speed of over 20 miles per hour, gradually cutting the stone like a string cuts cheese. Thanks to a water cooling system, the cut is even and smooth, without cracks. Another method is drilling vertical and horizontal holes in the rock, through which a diamond wire is then threaded. This forms the rectangular contour of the block. When the cuts are connected, a huge piece of marble, usually weighing from 20 to 50 tons, is separated from the mountain massif. It is propped up with hydraulic jacks, steel wedges are inserted, and the block is gradually released, preventing a sudden fall. Next, the blocks are transported from the quarry to processing plants. On the slopes of mountains, powerful tracked loaders and platforms on heavy trailers are often used for this. In mountainous areas where there are no roads, marble is sometimes lowered by special cable systems, a kind of funicular that leads from the quarry to the valley. In the workshops, the blocks are cut into slabs or blanks. For this, gang saws are used, large frame machines with dozens of steel blades, between which an abrasive mixture with water is fed. In modern production, they have been replaced by diamond circular saws, or laser cutting machines. The cutting accuracy reaches fractions of a millimeter. After cutting, the surface of the slabs is ground with abrasive stones of different grits, gradually moving from rough grinding to mirror polishing. If the marble is intended for architectural projects, it is further strengthened. A thin layer of resin or fiberglass is applied to the backside. This prevents chipping during transportation and installation. For sculptures, such reinforcement is not done. On the contrary, they look for a stone with a uniform texture without microcracks. Polishing is a separate art. It is performed on large machines where a series of round abrasive discs pass over the surface, gradually giving it a deep shine. To achieve a perfect effect, powders of tin or cerium oxide are used. It is they who reveal the structure of calcite, and the marble begins to play with reflected light. After polishing, the marble slabs are marked and sorted by color, pattern, and quality. Part of it is sent for export, another part to workshops for carving, facing, or manufacturing architectural details. Sculptors work with marble much more delicately. They use hand chisels, hammers, and now, pneumatic tools that allow them to carefully remove the stone layer by layer. Even with modern technologies, the art of marble processing remains semi-artisanal. It requires an eye, a touch, and an understanding of how the rock behaves. At the end, the marble products are coated with protective waxes or silicone impregnations, which enhance the shine and protect the surface from moisture. For interior work, softer compositions are used. For facades, water-repellent, UV-resistant ones. Quarries are usually located in mountainous areas that are difficult to reach. To cut blocks weighing from 20 to 50 tons, expensive equipment is needed. Diamond wires, cranes, hydraulic jacks. At the same time, about 30 or 40% of the quarried stone is suitable for commercial use. The rest is cracked or defective blocks that go to waste or are crushed into crumb. Due to the mass and fragility of the slabs, they are transported on special trailers or containers with cushioning. For imported marble, delivery can account for up to 30% of the final price. Every year, billions of bolts get manufactured worldwide, so many that you could wrap them around the Earth thousands of times. But hidden in that ocean of metal, there are a select few that cost hundreds of dollars apiece, and literally have lives depending on them. Today, I'm taking you to a place where an ordinary bolt transforms into something far greater. A component that withstands extreme temperatures, crushing pressure, and even the vacuum of space. There's no factory noise here, but there is something else. Something they don't talk about openly. And if you stick around till the end, you'll understand why a $500 price tag is just the tip of the iceberg. The first thing that hits you right when you walk in? Silence. For some reason, I was expecting noise, like you'd get in a regular machine shop. But here, everything's calm. A few machines, 3 or 4 operators, and this feeling like you didn't just walk into a factory, you walked into a lab. Actually, that's exactly what it is. A lab. That also happens to be a factory. Let me walk you through how every bolt begins. The raw material is a specific nickel-chromium alloy that has to be ordered ahead of time and arrives in rods about 3/4 of an inch in diameter. One of those rods weighs around 20 pounds. It costs roughly $250, and that's before anyone's even touched it. The material isn't chosen randomly. It can withstand temperatures up to 2,000 degrees Fahrenheit, won't deform under pressure of 150,000 pounds per square inch. And here's the kicker. It doesn't lose toughness, meaning it won't go brittle like glass. A regular semi rumbles down the highway. Nothing special, no markings whatsoever. Thousands just like it roll through Connecticut every day. Inside, on wooden pallets bound with metal straps, lie the rods. Not dumped in a heap, not just thrown together, each layer separated by wooden spacers so the rods don't touch or scratch each other. Because a scratch on the raw material surface is already a detected defect that later gets damaged or cut away. One pallet, typically 40 to 60 rods, depending on length. A pallet like that weighs around 1,200 pounds. The truck can carry 6 to 8 of these pallets, meaning one trip hauls roughly $80,000 worth of material. Yet the truck itself looks no different from one hauling pens to a supermarket. At the factory, the truck backs into the loading dock, a small bay with a single door, sized specifically for one trailer. The driver backs up, the dock locks click into place, and then the forklift takes over. The operator grabs the pallet, hauls it to the raw material warehouse, a separate room with controlled temperature and humidity, because the alloy can't pick up moisture before processing. There, each pallet gets a paper tag with the batch number, delivery date, and material certificate, a document from the supplier listing the exact chemical composition of that specific melt. Without that certificate, the bars don't even make it into the plant. The driver can wait at the gate all day. And this is where things get interesting. The stuff you don't see from the outside. Before a bar hits the machine, they cut off a small chunk, about an inch long, and send it to the in-house lab for incoming inspection. They check hardness, examine the structure under a microscope, sometimes run a spectral analysis. Takes 2 to 4 hours. Only after the lab gives the green light does the batch get accepted and move into production. If the result doesn't match the certificate, they return everything, even if the difference is minimal. They cut a blank from the bar stock. A CNC machine removes material layer by layer. One blank is roughly 4 inches long. Cutting takes about 20 minutes per piece, and during that time, the machine makes approximately 2,000 individual movements with different tools. The chips that remain get collected. They're worth money too. Next, heat treatment. The blank goes into a furnace and holds at 1,750 degrees Fahrenheit for 4 hours. This is what's called annealing, a process that relieves internal stress in the metal that built up during cutting. Skip this step, and the bolt can have micro cracks invisible to the naked eye, but under load, they become a big problem. After the furnace, the blank gets cooled down, not in cold water, not in open air, but in specialized chambers with a controlled atmosphere where the temperature drops at a rate of 50 degrees per hour. The entire cooling cycle? That's another 8 hours. Now here's where it gets interesting. thread cutting. The threads on these bolts aren't standard. They're engineered for a specific application, and in some cases are the customer's own proprietary design. The thread pitch might be, say, 28 threads per inch. That's an extremely fine pitch, ensuring maximum load distributed across the entire length of contact. Thread cutting is done on that same CNC machine, but now with a different tool, a carbide-coated threading tap. Cutting speed here is super low, around 30 revolutions per minute. Nothing gets rushed here. After the threads are cut, every bolt gets checked with a thread gauge. If the gauge goes in with the right amount of force, good. If it's too easy or too tight, the bolt goes back for rework or gets scrapped. If a bolt fails inspection, they don't try to fix it. They just start making a new one. Next up, final mechanical finishing. That's polishing the seating surfaces. Under the bolt head, there's a ring zone about 3/60ths of an inch wide that gets smoothed down to a surface roughness of 2 microinches. That's 50 times thinner than a human hair. For comparison, your average bolt from the hardware store has a roughness anywhere from 100 to 200 microinches, and nobody bats an eye. But here, this zone carries contact stress after the bolt gets tightened, and if it's uneven, microscopic movement can start, fretting as engineers call it, and over time the bolt will loosen. Can you imagine? Such massive work, but it's like jewelry. The coating is a whole separate deal. The entire bolt gets a nickel coating, 1 to 2 thousandths of an inch thick, through electrodeposition. Parts get dunked in a solution bath, and a direct current runs through it. Nickel gradually settles onto the surface in an even layer, about 20 millionths of an inch per year. The whole procedure takes 3 to 6 years, depending on the thickness required. After that, they check it, measuring thickness with an ultrasonic probe at 2 to 4 points across the bolt's surface. If there's more than a 10% deviation anywhere from spec, the bolt goes back for recoating. Now, where do these bolts actually go? Aviation is one of the main buyers, engine and landing gear fasteners. Then there are submersibles, where threaded connections have to handle pressure at depths of several thousand feet without corroding. There are clients from the nuclear industry. And there are a few projects in the space sector the factory doesn't really want to talk about. They just say, limited disclosure contract, and smile. When I asked how many bolts they make per day, the answer surprised me. 20 to 50 pieces. That's it. The factory doesn't chase productivity records, but each bolt passes through an operator's hands at least 7 times during the production cycle, which takes a total of 3 to 5 working days. Some bolts take a week to make, if the customer wants X-ray inspection and fatigue testing on top. That's a separate procedure. They load the bolt cyclically, 100,000 tension and compression cycles, watching for any cracks. I asked one of the operators if this all seemed like overkill for a bolt. He looked at me without much emotion and said, "This isn't a bolt. It's a system component whose failure costs more than our entire factory." Short and to the point. So there's your $500 a piece. And after that tour, I don't think it's expensive anymore. You're the best. Subscribe so you don't miss the next factory. It's gonna be even more interesting. Drop a comment saying where you're from, and maybe next time I'll swing by your state. Every year, machines are built around the world so massive and powerful that a single one could supply electricity to an entire city, and costs as much as dozens of private jets. But what if I told you that inside this colossal structure, there are parts machined with precision, thinner than a human hair, and that one tiny mistake could cost millions of dollars or even destroy everything? Today we're going inside a place almost no one gets to see, the heart of turbine manufacturing. And trust me, what you're about to see will completely change how you think about engineering, if you stick around till the end. Let's start with the fact that there are 2 main types of these turbines, and they work on very different principles. First, the steam turbine. You'll find these at nuclear and thermal power plants, on massive tankers and icebreakers. Second, the gas turbine. It's more like a giant jet engine without wings and lives mostly at gas-fired power plants and on some military vessels. Here at the factory they make both types, but we're heading first to the steam ones because they're older, more massive, and look like they were invented 2 centuries ago. Which, actually, they were, but they're still very much around. How a steam turbine works: short and formula-free. There's a boiler that heats water into pressurized steam at anywhere from 800 to 3,000 pounds per square inch. This steam, hot, pressurized, angry, blasts through nozzles onto rotor blades. The blades start spinning. The rotor spins the shaft. The shaft spins a generator or a ship's propeller. The steam cools down, condenses back into water, and returns to the boiler. The cycle is closed. Sounds simple, but for this simple not to explode into pieces and to run for 3 years without major repairs, you need all of this around me. The first shop they take me to is the foundry. This is where every turbine begins. The casing, the outer shell that holds all the internal components under pressure, is cast from alloy steel or cast iron, depending on operating parameters. For steam turbines in large power plants, the casing is cast in 2 or 3 tiers, and each tier is a separate mold. The mass of 1/2 of a casing can reach 60 to 80 tons. The metal is melted in arc furnaces with a capacity of 50 to 150 tons of molten metal, and the temperature there is around 5,000 degrees Fahrenheit. The mold for a large casing is a pit in the floor, 6 to 10 feet deep, lined with refractory clay. The metal is poured through a system of channels, and the entire process of filling one large mold takes 15 to 30 minutes. Then the casting cools, naturally from several days to 2 weeks, depending on the mass. After cooling, the casting goes to its first inspection. Ultrasonic testing searches for voids and inclusions inside, spots where the metal didn't fuse the way it should. X-rays check critical zones. If they find something significant, the casting goes back to remelt. No compromises. The rejection rate at this stage runs 3 to 8% depending on the casting's complexity, and that's completely normal for parts this size. Next, machining. Now, here in the shop floor, there are machines that made my jaw drop. The horizontal boring mill that machines the inner casing surface. It's about 60 feet long. The table where the part sits moves. The spindle stays put. The tool freely bores the bearing and seal mounting surfaces to an accuracy of plus or minus 0.5 of an inch. Why so precise? Because the rotor spinning inside at 1500 to 3600 revolutions per minute has a clearance between its blades and the casing of 50 to 150 microinches. 1% efficiency loss at a large power plant. That's millions of dollars in extra fuel costs per year. The rotor is the star of this story. It's a shaft carrying discs with blades, and it's the most complex part of the entire turbine. The shaft for a large steam turbine is a forging made from special chromium molybdenum vanadium steel, 20 to 40 feet long and weighing 20 to 60 tons in its rough state. A forging means you take a red-hot ingot of metal and just hammer it with a press weighing 5,000 to 50,000 tons to give it the shape you need. The grain structure of the metal during forging gets oriented along the shaft's axis. That's how you achieve torsional strength. After forging, the shaft goes through heat treatment again, then heads to the machine shop. Turning takes 2 to 4 weeks of continuous work on a lathe that's nearly 70 feet long. Chips fly, coolant flows, and machining away from that massive blank reveals the sleek shaft you saw in the drawings. This is the part where I'm always amazed. A gigantic component, yet precision like a watch mechanism. Blades are a separate production line. Steam turbines at large power plants have anywhere from 8 to 20 stages, and each stage is a disc with blades. First stage blades are small, sometimes less than 2 inches tall, because the steam there is still under high pressure and dense. Last stage blades are massive, up to 5 or 6 feet long on the largest turbines. These blades are forged and milled from iron-based alloys or stainless steel, and in their final profile, they have an aerodynamic shape with precision to within plus or minus 0.02 of an inch along the entire length. Each blade is checked for resonant frequency. It can't match the operating rotational frequency of the rotor, or else after a few thousand hours, a fatigue crack will develop from vibration. How they test this is simple. They tap the blade with a small hammer and listen with a special acoustic sensor. A very elegant method for such a serious problem. Assembling the rotor. This is when it starts to feel like an operating room. Bladed discs get mounted onto the shaft using shrink fitting. The disc gets heated to 300 to 400 degrees Fahrenheit. It expands, slides onto the shaft, then cools and grips the shaft with a force no bolt could ever match. No threads, no glue, just temperature difference and precision sizing. The interference fit when cold, 1 to 3/1000 of an inch per inch of diameter. After assembly, the rotor gets balanced, and this takes 1 to 3 days. Balancing happens on a specialized rig, where the shaft spins on bearings while sensors register vibration. If there's any imbalance, metal gets removed from certain spots, or balancing inserts get installed. Allowable residual vibration on a large rotor, fractions of an ounce per inch of radius. If you think that's strict, you're thinking right. After assembly, the turbine heads to the test stand. At full operating parameters, pressure and temperature, they run the turbine for 24 to 72 hours. Sensors track bearing temperatures, vibration, steam leaks, power output. If anything goes outside the limits, stop, disassemble, analyze. There have been cases where they found a defect here that the X-ray missed initially. So the test stand isn't just a formality. It's the last line of defense before shipping. The finished turbine gets broken down into transport blocks, casing separate, rotor separate, auxiliary equipment separate. A large turbine rotor travels on a special trailer with hydraulic suspension, the kind you've seen on YouTube, with 18 axles moving at 20 miles per year. They coordinate the route a month in advance. Every bridge height and every turn width needs checking from the factory to the port or customer. Sometimes for one of these transports, they temporarily remove road signs and even take down power lines over the highway. I asked the chief engineer how many turbines they build per year. He said 12 to 20 of various types. That's it. Less than 2 per month. But each one runs for 30 to 50 years and generates electricity for hundreds of thousands of people every day. Some things don't need high-volume production. What if I told you that a high-speed train wheel experiences temperatures hot enough to make metal glow, and still can't afford to fail? Why must this piece of steel withstand tests that would destroy any car wheel in seconds? There's a reason almost nobody suspects, and if you stay with me through to the finale, you'll discover the secret process that forces the wheel to survive where other metal simply melts. But first, tell me, does your country actually manufacture railway wheels? Or are they imported? A train rockets down the tracks at over 186 miles per hour. At that speed, an ordinary wheel would simply disintegrate. Why? Because it has to withstand not just weight, but a whole series of inhuman trials. The material is everything. This isn't ordinary steel used for silverware or even car bodies. High-speed train wheels are made from a special grade of steel, melted according to a unique, meticulously refined recipe. This recipe is a combination of iron with specific alloying elements, manganese, silicon, chromium, molybdenum, that give the steel extraordinary strength, toughness, the ability to absorb impacts without failing, and endurance. Beyond that, this steel must be as pure as possible, free of any foreign impurities that could become a weak point. After the special steel is melted in massive metallurgical furnaces, it's poured into molds to create large steel billets, what we call slabs or blooms. But that's just the beginning. The real transformation starts in the forging shop. This is where one of the most powerful forging presses comes into play, along with specialized forging machines. The billet, heated until it glows bright yellow or red, that's around 2000 degrees Fahrenheit, is fed under the press. The process involves multi-stage forging. It's not a single strike, but rather a whole series of controlled pressures and rotations. The giant hammers, or jaws of the press, slowly, yet with unstoppable force, flatten and shape the red-hot metal. First stage, the billet is compressed to give it a rough circular shape, densifying the metal and eliminating internal voids. Second stage, the material is flattened and rolled, forming a disc with a central hole. This is where the future wheel's outline begins to emerge, with its rim, disc, and hub. This directional metal flow shapes its internal fibrous structure, making the wheel exceptionally strong in the required directions. Forging, unlike casting, transforms steel's microstructure. It compresses the metal's grains, eliminates casting defects, and creates a directional fibrous structure that gives the wheel exceptional strength and fatigue resistance. It's like an athlete's muscles. After training, they become stronger and more resilient. Why such complexity? Because high-speed train wheels operate under extreme conditions that are hard to imagine. When moving at speeds over 186 miles per hour, the wheel's surface heats up from friction against the rails and brake pads to nearly 2,000 degrees Fahrenheit. That's the temperature at which metal begins to glow red and change its properties. And this heating isn't constant. It's cyclical. Heating during acceleration and braking, cooling during movement. The material must withstand these constant temperature fluctuations without forming microcracks, which over time can lead to failure. Each pair of wheels carries a load of dozens of tons. A single railcar can weigh between 50 and 70 tons, and this weight is distributed across just 4 wheels, that is, 2 wheel sets. This creates constant pressure acting on the wheel. The train doesn't ride on a perfectly smooth surface. It crosses rail joints, uneven sections, and switches, which generate continuous impact loads. The wheel must be incredibly tough to absorb these shocks without cracking or breaking apart. After forging, the wheels aren't finished yet. They undergo complex heat treatment, which is key to developing their final properties. The wheel centers, the discs that connect the hub to the rim, are hardened. Hardening is a process of heating steel to high temperatures, then rapidly cooling it. This makes the metal harder and stronger. But hardening makes the metal brittle, so it's always followed by tempering, reheating to a lower temperature with slow cooling. Tempering reduces brittleness and improves toughness while maintaining high strength. This combination of hardening and tempering creates the ideal steel microstructure that can withstand extreme operating conditions. But even after all these complex processes, no wheel reaches the rails without brutal yet necessary testing. Every single wheel, without exception, undergoes ruthless inspections. Ultrasonic testing. It's like medical ultrasound diagnostics, but for metal. Special sensors send high-frequency ultrasonic waves through the wheel. If there's even a microscopic crack, void, or defect inside, the ultrasonic wave bounces off it and creates an echo that the instrument captures. This method allows us to see internal defects without destroying the wheels. A defect the thickness of a human hair is already grounds for rejection. Magnetic particle inspection. The wheel gets magnetized, then its surface is coated with fine ferromagnetic powder. If there's a crack, even one invisible to the naked eye, it distorts the magnetic field, and the powder concentrates along that crack, making it visible. This reveals even the tiniest surface defects that could become failure points during operation. Only wheels with perfect structure and zero defects are cleared for installation on high-speed trains. This isn't engineering perfectionism. It's about the safety of thousands of passengers who trust their lives to these metal giants. While the United States isn't leading high-speed rail development like China or Japan, its rail network remains one of the world's largest, and American manufacturers have extensive experience producing high-quality wheels for various rolling stock, passenger trains, freight locomotives, and switching equipment alike. Unlike the automotive industry, where thousands of companies manufacture parts, the railroad wheel manufacturing market in the US is significantly more concentrated. This is a highly specialized field, requiring massive investments in metallurgical equipment, forging presses, and quality control systems. The two main and most powerful players in the North American railroad wheel manufacturing market are Amstead Rail and KF USA. While KF is a Spanish company, it maintains production facilities in the United States to meet local demand. Previously, other major manufacturers existed, but the market has consolidated. Total annual railroad wheel production in the US fluctuates, but can be estimated in the range of 300,000 to 500,000 units per year. This figure includes wheels for all types of rolling stock. It's worth noting that while the US can manufacture wheels capable of withstanding high speeds, the actual demand for wheels designed for continuous operation above 186 miles per hour remains relatively limited due to the scarce number of true high-speed rail lines in the country. For instance, Amtrak's Acela Express trains, running along the Northeast Corridor, reach speeds up to 150 miles per hour on certain segments, but not beyond the aforementioned threshold of 186 miles per hour, which requires specific material and design standards. However, US wheel manufacturing technologies and standards do enable production that meets international requirements for high-speed trains should the need arise. From a material standpoint, American manufacturers, like their global counterparts, utilize specialized grades of carbon steel alloyed with manganese, silicon, and other elements to achieve the necessary strength, wear resistance, and toughness. Forging, heat treatment, and non-destructive testing processes are standard and comply with the highest international safety and quality benchmarks. Every year around the world, billions of tons of rock are blasted apart with explosives. Tunnels are carved straight through mountains, and rockets are launched into the sky. But few have ever seen the place where the force capable of reshaping landscapes in seconds is born. Today, we gained access to one of the most tightly guarded industrial facilities, where chemistry, fire, and metal come together to create the legendary TNT, the very substance whose explosive power became the world standard. But the scariest and most fascinating part isn't the explosion itself. It's how this yellow powder makes its journey from an ordinary liquid to a material that can obliterate a house-sized boulder. And trust me, if you stick around until the end, you'll learn a fact about TNT production that will completely change how you see modern industry. TNT, or trinitrotoluene as it's also called, showed up way back in the 18th century when chemists started messing around with toluene. Americans call it TNT, short for trinitrotoluene, and to this day, it's the gold standard. 1 gram of TNT, the unit for measuring explosive force. Here at the plant, everything starts with massive tanks of toluene. This liquid flows into reactors, giant stainless steel vessels, where the temperature holds steady at 400 to 480 degrees Fahrenheit. No, seriously, it's hell in there. 200 to 250 degrees Celsius if you convert it. A mixture of nitric and sulfuric acids gets pumped inside. Concentrates so harsh, they'll melt your gloves right off. The nitration process runs anywhere from 3 hours to several days. First you get mononitrotoluene, then dinitrotoluene, and finally trinitro. The acids circulate in a closed loop. They get recycled instead of just dumping them into the ground. Operators in protective gear monitor the gauges, pressure, temperature, concentration. Everything's under control because the slightest shift and the reaction can go sideways. From the reactor, the mixture heads to coolers, long coiled tubes where the hot TNT crystallizes. Then settling tanks. The heavy TNT sinks to the bottom, while the lighter acids get drained off. That jelly-like mass right there, that's raw TNT, still wet with acid. They wash it with hot water at 150 to 180 degrees Fahrenheit to neutralize what's left. The water drains into the sewage system, and the crystals get dried in vacuum ovens, rotating drums that spin like washing machines. Massive stainless steel vats get pumped full of water at temperatures between 150 and 180 degrees Fahrenheit. The water jets out like in an industrial laundry, washing away residual nitric and sulfuric acid. TNT floats in it like jelly in boiling water, spinning, giving up impurities. The process takes half an hour. The water changes 3 times because the first batch is yellow from acid, the second is cloudy, and the third is already clear as a tear. This water doesn't just go down the drain. It gets neutralized with lime in basins, filtered through a 10-foot thick layer of sand, and then released into the river. Ecology stays under control because acid is poison for fish. Meanwhile, the crystals get unloaded. The mass becomes solid, but still 6 to 10% wet. Now comes the drying, the most interesting part. The entrance to this vacuum oven, a room where 20 rotary drums hum, each about 6 feet in diameter. TNT gets shoveled in there, 200 pounds at a time. The drum seals shut, air pumps out until pressure drops to 100 millimeters of mercury, and heating kicks in, 130 to 140 degrees Fahrenheit. Fans blast hot air through the center. The drum spins at 30 rotations per minute, like a washing machine on spin cycle. Crystals tumble, dry evenly, don't stick to the walls. 2 hours, and the doors swing open. Pure yellow powder, temperature 40 degrees, moisture content 0.5%. A worker in a mask pours it into hoppers, where a conveyor will carry it off to granulation. 5 tons per shift from one drum, and no dust because the vacuum pulls everything into filters. The operator jokes, "Dry as my sense of humor." Without this step, TNT would clump together or detonate from moisture. An hour or two, and we've got pure yellow powder. Color? Light yellow to dark orange, depends on purity. Here we get the top grade, 98% pure product. Next up, granulation. The powder gets moistened, pressed into briquettes the size of a matchbox, then crushed down to granules 2 or 5 thousandths of an inch in diameter. Why granules? Because the powder's easier to pack, doesn't create dust, and detonates evenly. I peer into the press, a giant machine with pistons pushing 200 atmospheres of pressure, and the briquettes come out hard as rock. Then the grinders, hammer mills where the shafts spin at 6,000 revolutions per minute. Dust gets vacuumed out by ventilation, because breathing in TNT, that's gonna cost you. Now packaging. Granules pour into airtight cardboard boxes weighing 100 pounds each. That's the standard for quarries and the military. Every box gets checked for moisture. No more than 0.70%, otherwise the TNT sweats and becomes sensitive. There are also barrel forms for underwater blasts. There the granules get mixed with paraffin so they don't get wet. Boxes are sealed, marked by lot, and done. Off to the warehouse. From here, TNT ships out to quarries, mines, defense. One box is enough to blast through 200 tons of rock. And then there's friction sensitivity. The cylinder spins for 6 hours, and if it doesn't blow, we're good. Lab techs in masks check purity with a chromatograph. Toluene or acid impurities aren't allowed. Nothing but respect. These people handle explosives like jewelers. Production is massive. 1,000 tons a month, that's millions of pounds. Energy? Electricity from gas turbines, steam from their own boilers. Waste. Acids get regenerated. Toluene gets redistilled. Environment? Filters on a 200-foot smokestack. Wastewater treated until it's clear. Neighbors don't complain. The plant sits 10 miles from the nearest town. Fun fact, TNT doesn't just explode. They melt it at 82 degrees Celsius, 250 Fahrenheit, and pour it into shells like hot wax. Or mix it with gunpowder for plastic charges. In quarries, 1 ton can shatter rock the size of a 3-story building. In mining, you can't punch through a mile-long tunnel without it. And in the military, it's the backbone of torpedoes, mines, bombs. You know how much steel came into this plant? Thousands of tons. Reactors made of chrome molybdenum steel, because regular steel just gets eaten alive by acids. I'm standing in the granulation shop right now. Hear that press rumbling? See those granules pouring into bins like golden sand? The air's clean, but it smells like nitrocellulose. Familiar scent if you've ever been to a powder plant. The operator laughs. Don't breathe too deep, or you'll detonate yourself. Joking, obviously. But the discipline? Ironclad. 8-hour shifts. Lunch break with the clatter of spoons on metal trays. Compare that to the old plants. Back then, everything by hand. Women in skirts packing TNT with bare hands. Explosions once a month. Now, robotic arms, sensors, cameras. Evolution. One worker monitors 10 processes from a control panel. And the pay? Competitive. The plant's like a living organism, roaring, churning, producing power. TNT isn't evil, it's a tool. Builds roads, digs mines, defends the country. Without it, no 1,000-foot bridges, no tunnels under mountains. Without this unassuming rock, often mistaken for ordinary dark pebbles or heavy chunks of granite, modern electronics would instantly collapse into a pile of useless plastic and silicon. Tin ore, or more precisely its primary mineral, cassiterite, is the hidden foundation holding up our entire digital world. When we talk about high-tech, we name-drop gold or complex semiconductors, but this is the invisible glue binding billions of microscopic components into a single working system. Tin's journey begins deep in the planet's crust, where for millions of years, metal-rich solutions seeped into fractures in the earth, forming deposits that today drive the pace of human progress. Cassiterite, often called tinstone, has an incredible density and a distinctive diamond-like luster when fractured, though on the outside, it can look like ordinary brown or black rock. Mining this ore demands massive effort and specialized knowledge. The world's major reserves are concentrated in what's called the Tin Belt, stretching through Southeast Asia, China, Latin America, and Africa. The scale of extraction is staggering in its variety, from colossal open-pit mines and underground shafts to dredging operations on the ocean shelf. For example, off the coast of Indonesia, giant floating dredge factories pull up thousands of tons of tin-bearing sand from the seafloor, sifting it through complex filter systems to separate out the heavy ore particles. The process of transforming rock into pure metal is long and exhausting. Since tin content in ore is now low, the rock first undergoes multi-stage enrichment. It's crushed, washed, and separated using gravity methods that exploit cassiterite's high specific gravity. After obtaining the concentrate, the smelting stage begins in a furnace at around 2,200 degrees Fahrenheit. Here, under the influence of reducing agents, tin separates from oxygen and other impurities, transforming into a liquid silvery metal. But for the electronics industry's needs, this purity isn't enough. The metal goes through a series of refining processes to eliminate the tiniest traces of iron, copper, arsenic, or antimony. Only after this does it become the material we see in the form of solder. Solder. That's the main use for tin in the modern world. It's not just some auxiliary material. It's a critically important component of any electronic device. Previously, soldering used an alloy of tin with lead, but due to environmental requirements and health safety concerns, the world switched to lead-free technologies. Today, the latest circuit boards are joined using alloys where tin makes up 95 or even 99%. Every smartphone, laptop, control unit in cars, or satellite onboard computer contains several thousand soldered connections. Without tin's ability to wet the surfaces of other metals and create reliable electrical contact at low temperatures, mass production of electronics would be impossible. Factories that produce modern electronics operate with incredible precision, and that's where a key tool comes into play. In surface mount assembly shops, specialized machines deposit solder paste through stencils onto circuit boards with accuracy down to the micron. Then the board passes through reflow ovens, where the paste transforms into solid metallic connections. It's an automated process where every second and every milligram of metal matters. If the tin contains even minor foreign impurities, it can lead to microcracks or tin whiskers, thin thread-like crystals that grow from the solder and can cause short circuits. That's exactly why quality requirements for tin ore and purification methods keep getting stricter. The impact of tin on urban development and global energy is hard to overstate. Sure, we don't build house frames from this stuff, but it's in every lighting control system, every elevator, every safety sensor. The growth of smart cities relies entirely on billions of sensors and controllers, each one held together by tin solder. This makes it a critical strategic resource, with entire regions shaping their economic policy around the battle for control over its deposits. Countries with major cassiterite reserves become key players in the high-tech supply chain. But tin ore extraction comes with serious challenges. Deep open pits and seabed dredging reshape ecosystems, demanding strict reclamation standards. Responsible companies try to minimize environmental impact by restoring forests and cleaning water used in the refinement process. At the same time, recycling is playing a bigger role. Tin is a metal that can be cycled back infinitely. Recycling old circuit boards keeps the metal's high purity with way less energy than mining it from ore. This creates a closed-loop economy, where yesterday's shattered screen becomes the source material for a new device. Interesting fact, tin's been used for millennia. When it combined with copper to create bronze, it gave an entire era of human history its name. Back then, tin was hunted down as aggressively as we hunt for oil or gas today. But while ancient people made swords and cookware with it, today it's become a tool for transmitting information. That's the evolution of this metal's role. From the brute force of bronze weapons to the refined precision of a silicon chip, where tin provides the pathway for electrons to flow. The stone once prized for its ability to make copper hard is now valued for its malleability and conductivity in the micro-world. Technological progress demands ever-increasing quantities of this metal. The growth of renewable energy, solar panels, and electric vehicles creates additional demand. Each photovoltaic panel requires tin connections to harvest the sun's energy. Electric vehicles contain significantly more electronic components than internal combustion engine cars, making this element essential in the fight for climate neutrality. Thus, ancient cassiterite becomes fuel for the green revolution. It's crucial to understand that tin deposits are distributed extremely unevenly across the planet. This creates certain risks for global production stability. Any disruptions in ore supply from major mining regions instantly impact consumer technology worldwide. This pushes scientists to search for new methods of enriching even low-grade ores, as well as developing technology for extraction from deeper horizons. Every foot of new mine shaft, or every mile of surveyed deposit, is a guarantee that factories keep producing new devices, and the planet's digital network continues to expand. The transformation of tin from mountain rock to solder on a circuit board is an example of how humanity has learned to harness the special properties of materials to achieve remarkable results. It's about tin's ability to be the connecting link. When we look at a chunk of tin ore, we see not just a mineral, but the potential for millions of conversations, terabytes of transmitted data, and the operation of complex mechanisms that ensure our comfort. Tin remains a humble yet irreplaceable hero of the industrial stage, working where no one sees it, at the very heart of machines. Production chains that begin in quarries and end in the clean rooms of high-tech factories are testament to our global interdependence. Tin isn't just a detail on a circuit board, it's the backbone of economies across continents. The continuous flow of ore, concentrate, and finished metal is the circulatory system of industry. Every ton of cassiterite pulled from the earth passes through the hands of thousands of specialists before becoming part of our global information infrastructure. And as we move toward even greater automation and digitization, the role of this stone will only grow, proving that great achievements often start with very small but critically important details. So, tin ore is the real key to modernity. It teaches us to value resources that seem invisible, but without them, the world we know would cease to exist. This is a story about how nature gives us materials, and human ingenuity finds the perfect use for them, transforming heavy ore into the lightness of wireless communication and the speed of data processing. Every grain of cassiterite carries its contribution to global development, remaining an eternal reminder that high technology has its roots in the work of the Earth, a stone-born origin. From dark depths to gleaming device cases, the journey of tin is the journey of progress itself. Every 3 seconds worldwide, a new engine block rolls off the production line, the heart of a car that will withstand millions of explosions, temperatures over 4,600 degrees, and operate for decades without stopping. But how do you transform molten metal into a perfect mechanism with precision down to a micron? One mistaken dimension, and the engine will tear itself apart within minutes of operation. Every year, over 100 million of these blocks are manufactured, and each one goes through a hellish birthing process. Molten metal at 5,400 degrees, sand molds that self-destruct, and robots that cut channels thinner than a human hair. But there's one secret the manufacturers don't talk about. A mystery hidden inside every block that determines whether your car will go 60,000 miles or 600,000. Stay until the end. What you'll learn will forever change how you see what's happening under your car's hood. Let's start by understanding what an engine block actually is. It's the foundation that holds the entire engine together. Inside it are the cylinders where fuel combustion occurs, pistons that move up and down, and other critical components. The engine block must be strong, lightweight, and resistant to high temperatures. That's why manufacturing it is a complex process that demands precision and advanced technology. Everything begins with an idea. Engineers develop a concept for an engine that must be powerful, economical, and environmentally friendly. They use specialized 3D modeling software to create a digital model of the block. This allows them to account for every detail and test how the engine will perform under various conditions. Engine blocks are made from different materials, but the most common are cast iron and aluminum. Cast iron is strong and resistant to high temperatures, but heavy. Aluminum is lighter and dissipates heat better, but less durable. Sometimes composite materials or alloys are used to combine the advantages of both metals. After the engineering team completes all calculations, computer modeling, and finally approves the design of the new engine block, the true heart of the future automobile, the most interesting part begins: its birth in metal. The first and perhaps oldest step in metallurgy is casting. A massive shop filled with the hum of machinery, the smell of molten metal, and the glow of high temperatures. This is the foundry, where engineers' dreams become real components. First, a mold for the block is created. There are two main approaches to creating these molds, each with its own advantages. The first, and most common for large-scale production, uses sand molds. This is an amazing, though traditional method. First, they make a pattern of the future engine block, usually manufactured from wood or metal, and it's an exact copy of the block, but accounting for certain features, such as compensation for metal shrinkage during cooling. Then this pattern is placed in a special container, where it's tightly packed with a mixture of quartz, sand, clay, and organic binding agents. This mixture is compacted, then baked or chemically hardened, creating a strong but porous mold. After this, the pattern is carefully removed, leaving a cavity that precisely matches the shape of the future block. The most challenging aspect of sand molds is creating internal cavities, coolant channels, oil passages, cylinder bores. For this, they use so-called cores, separate elements, also made from sand, that are inserted into the mold. After pouring the metal and cooling, the sand is easily removed, leaving the necessary internal channels. The advantage of sand molds is their relative affordability per unit at large volumes and the ability to create very complex internal geometries. The second method, often used for aluminum blocks or smaller production runs, uses metal molds or permanent molds. These are stronger, reusable molds made from steel or cast iron. They're more durable and allow for parts with smoother surfaces and higher dimensional accuracy right from the casting stage. However, metal molds are much more expensive to manufacture, and it's harder to adapt them for creating the very complex internal channels found in engine blocks. Therefore, they're often combined with sand cores for internal cavities. The chosen material, cast iron or aluminum, is melted in a furnace at high temperature. For cast iron, this is typically over 4,600 degrees Fahrenheit. For aluminum, around 3,000 degrees. In massive induction or arc furnaces, metal scrap and pure ingots slowly transform into a glowing, liquid mass that shines bright orange or silvery light. This process includes precise control of chemical composition. Metallurgists add special alloying elements, such as silicon, magnesium, copper, in strict accordance with the recipe, to give the future block necessary properties: strength, wear resistance, lightness. The molten metal is constantly stirred and goes through refining processes to remove unwanted impurities that could reduce the quality of the finished part. Finally, the climax arrives: pouring. The molten metal, radiating intense heat, is carefully transferred from the furnace into special ladles, then into the prepared molds. This is the moment of maximum concentration and precision. The metal must fill every cavity of the mold, displacing air and completely matching its configuration. The pouring process can be gravitational, meaning the metal simply flows under gravity or under pressure, which ensures better mold filling and reduces porosity. After pouring, the mold remains for some time, so the metal can cool and solidify. This can take from several minutes to several hours, depending on the block size and metal type. When the metal has cooled and fully crystallized, the next stage occurs. The mold is broken apart. If it's a sand mold, it's simply destroyed using vibration or hydraulic hammers, freeing the newly created metal object. The sand is later collected and partially recycled. If it's a metal mold, it's opened and the finished block is carefully extracted. As a result of this process, we get what's called a rough engine block. It's not perfect yet. Its surface is rough, it may have sand residue or so-called flash, small metal overflows at the mold seams. It doesn't yet have mounting holes, and it lacks the micron tolerances required for engine operation. But it's already a real block, massive and heavy if it's cast iron, or surprisingly light if aluminum, but already with a clearly defined shape, ready for the next processing stages that will transform it into a high-precision part capable of withstanding incredible loads inside the engine. Mechanical processing is performed on specialized computer numerically controlled machines. The large, solid block is secured on a special table. Around it, various tools move, performing their work. Like a scene from some movie, isn't it? Let's start with the most obvious: cylinder bores. These holes must be perfectly round, have precise diameter, and be positioned exactly on one axis, since pistons will move within them. First, machines use large end mills to roughly remove material, creating preliminary holes. It's like carving out a large chunk from cheese. Then more precise tools come into play. Special boring cutters are used, which carefully remove the thinnest layers of metal, bringing cylinder diameters to the required size. This happens in stages, with constant dimension control. After this, cylinder walls undergo honing. This is final abrasive processing that creates very fine, cross-hatched scratches on the internal surface. These scratches retain lubricant, ensuring perfect lubrication of piston rings and minimizing friction, which is critically important for engine efficiency and longevity. Actually, the cylinder surface after this processing feels perfectly smooth to the touch, but under a microscope has the perfect structure for retaining an oil film. Next, oil and cooling channels. These systems that penetrate the entire block are vitally important. Oil channels deliver lubricant to all moving engine parts, such as the crankshaft, camshaft, pistons, ensuring their lubrication and heat removal. Cooling channels circulate coolant, removing excess heat generated during fuel combustion and maintaining optimal engine operating temperature. The internal, complex labyrinths of coolant and oil channels, as we mentioned, are formed during the casting stage using sand cores. But after this, they need to be opened and brought to perfect condition. For this, high-precision drills and mills are used to create inlet and outlet openings for these channels, and also connect them with other engine parts. Each hole must be positioned with millimeter, or even micron precision, so fluids can circulate freely. Every year, over 1,000 giant ships are sent worldwide for scrapping, each weighing up to 50,000 tons and stretching nearly 3 football fields in length. It's like dismantling an entire floating city, with hundreds of miles of cables, tons of toxic substances, and metal worth millions of dollars. One mistake, and an environmental disaster is inevitable. But here's the most amazing part. Inside each of these massive vessels hides something that turns scrapping into a real treasure hunt. Workers risk their lives among plasma cutters and toxic fumes to extract these valuables. What exactly are they looking for? And why have some countries turned ship graveyards into a multi-billion-dollar business whose dark side everyone keeps quiet about? Stay tuned. What you'll learn next will make you look at every ship in port with completely different eyes. Why is ship recycling so important? Vessels that we typically imagine as enormous floating megastructures can be nearly 1,000 feet long. Their weight sometimes reaches tens of thousands of tons, making them among the largest man-made objects created for sea travel and cargo transportation. But beyond their massive dimensions, these ships have extremely complex internal structures. Hundreds of feet of cables, pipelines, shafts, and various safety and comfort systems, plus countless different elements and mechanisms that perform different functions. This entire architecture isn't just scrap metal, but a complex organism that must be very carefully and properly dismantled when the ship reaches the end of its service life. It's critically important to properly remove all hazardous substances from the vessel that may have accumulated during its operation. These can be bioactive substances, toxic paints, fuel residues, lubricants, chemicals that, if handled improperly, can contaminate the sea, soil, and air, causing serious environmental problems. Without proper preparation, dismantling such a vessel can turn into a natural disaster. However, scrapping these maritime giants also has a very bright positive side. The metal from which the ship is made is excellent and valuable raw material that can be recycled and returned to production. This metal is used for building houses, machines, construction structures, and also for creating new vessels. This way, it's possible to reduce the need for smelting new steel, save energy and resources, and also reduce the amount of waste. Metal recycling from ships becomes an important link in the closed loop of modern industrial economy. Scrapping such huge objects also makes it possible to free up ports where old ships are standing, so new, modern vessels can take their place. This allows optimizing the work of naval bases and promotes fleet renewal. Additionally, proper recycling helps reduce operational costs for maintaining old ships and improves environmental standards in the maritime industry overall. The ship is delivered to special ship graveyards. These are usually coastlines with shallow water or special slipways. These locations aren't chosen randomly. Shallow water coastlines allow easy approach of the ship to shore, where it can be safely moored and dismantling can begin. Often these are small bays or beaches where the giant vessel is specially brought, so it doesn't interfere with maritime traffic and doesn't damage port infrastructure. Slipways, in turn, are large platforms or special structures where the ship is placed for dismantling on land. They're equipped with everything necessary for convenient and safe work: crane equipment, metal cutting tools, waste removal systems. One of the main tasks for specialists is ensuring environmental safety. After all, during operation, the ship accumulated many substances that, if handled carelessly, can harm the environment. These can be not only lubricants and fuel residues, but also toxic paints or chemicals. Therefore, the entire dismantling process begins with removing all such substances. Fuels and lubricants are drained into special containers and taken away for recycling or disposal to avoid getting into water or soil. Similarly with electronics and furniture, everything that could potentially harm nature is removed as a priority. This stage requires speed and maximum caution so that environmental standards aren't violated. After the ship is cleared of all hazardous and household items, the direct dismantling of the hull begins. And this is the most complex and dangerous part. Using special plasma cutters and gas torches, large steel structures begin to be cut into small pieces. This involves both hand equipment and heavy machinery, cranes, lifts, special manipulators. Plasma cutting allows very precise, fast and efficient metal division that will later go for remelting. The dismantling process itself happens sequentially, stage by stage, starting with the most hard-to-reach or dangerous zones. Metal sheets, beams, decks, and internal partitions are carefully separated so as not to damage structures that might still be needed for analysis or recycling. The complexity is that giant elements are often unevenly distributed and may be under tension, and due to corrosion or hull deformation, some parts can unexpectedly drop or fall at any moment. It's also important to emphasize worker safety. During plasma cutting, hot sparks and toxic fumes arise, requiring special protection from workers, respirators, special clothing, and constant air monitoring. A small mistake or neglect of rules can lead to serious injuries and accidents. Therefore, at every step, the process is regulated by strict safety rules, and the entire site is covered by fire suppression systems and medical support. Dismantling the hull and main steel structures of the ship is, without doubt, an extremely important and complex stage of scrapping a giant vessel. However, after this large body of work is completed, the job doesn't end. Ahead lies another massive phase that requires no less attention and certain skill, as it concerns dismantling and sorting countless smaller, but no less valuable and complex materials. One of the most massive and complex processes is working with cables. The ship contains hundreds of miles of cable networks that provide power and communication between all systems. These are powerful steel cables with insulation made of plastic, rubber, and possibly using non-ferrous metals. Cables don't just remain at the recycling site, they're carefully removed, processed, and sorted. Separating the metal core from insulation materials makes it possible to send pure copper or aluminum for remelting, and the insulation layer for recycling as raw material for new polymers. Workers must act very carefully not to damage long cable pieces, and also observe safety techniques due to the presence of residual substances or rust. Another important category of materials is insulation materials that line or fill the ship's walls, technical rooms, and pipelines. Insulation is often made from special materials: mineral wool, polyurethane foam, or basalt wool. These substances help control temperature inside systems and ensure safety when working with hot or cold components. After removing insulation, it's sorted and sent to specialized enterprises where these materials can be recycled or disposed of without harming nature. Working with ventilation systems also requires thoroughness. Ventilation pipes and units that were used for air conditioning and circulation in different parts of the ship are dismantled and cleaned of dust, lubricant residues, or other substances. Metal elements of systems typically undergo quality remelting, and plastics or rubber often become raw materials for new products. Special attention is paid to water supply systems and sanitary installations. On board the ship are complex shut-off mechanisms, pipelines, fittings, mixers, tanks, and other equipment. Pipe parts and equipment are carefully separated, cleaned of sediment, lubricants, and other contaminants to be sent for remelting or appropriate recycling. After all, these materials may contain toxic substances, so their disposal or recycling happens strictly according to regulations. No less important is dismantling equipment from the engine room. There are engines, generators, pump systems, turbines, and other complex machinery that typically has significant weight and contains large amounts of metals, including non-ferrous ones. Such equipment is mainly repaired and reused or dismantled into parts, some of which undergo recycling. In individual cases, engines even go for sale as used spare parts, avoiding becoming scrap metal. Furniture, household appliances, lighting, and other interior items of the ship also aren't just thrown away. They're removed and sorted. Wooden, metal, or plastic parts undergo separate recycling or disposal. In some cases, furniture, if it's in good condition, is sold for reuse, and all paints, varnishes, and certain polymer materials are taken for environmental recycling to reduce pollution. What if I told you that inside the most dangerous machines on the planet hides a steel secret that can only be created once, and a mistake costs an entire nation? That there's an ingot that cools underground for 6 weeks and withstands pressure that would shatter mountains? This giant is born in fire, exceeding 5,000 degrees Fahrenheit, endures months of forging, blows of tens of thousands of tons, and thermal shocks that would explode ordinary metal into fragments. Stick around till the end. You'll discover what these monoliths are actually built for, and why, without them, the modern world would simply grind to a halt. It all starts in the foundry. To create a monolithic ingot, you need liquid steel of impeccable quality, poured into a mold in one continuous stream. This is a stage that demands maximum coordination, because we're talking about thousands of degrees and hundreds of tons of metal. A striking example of such an engineering feat was a record-breaking pour carried out by the British firm Sheffield Forgemasters in 2015. The company's metallurgists successfully handled the pouring of 607 tons of liquid steel into a giant casting pit. To put that volume in perspective, it's nearly the weight of a full-sized Airbus A380 passenger jet. The pouring process is critically important. The steel must not only be melted, but also purified to a level that meets the strictest customer requirements. For example, for reactor components. This means minimizing impurities, gases, and slag. A continuous pour ensures that there won't be any layered defects or boundaries in the ingot structure that would reduce its mechanical strength. During casting, the steel must be fully degassed. Oxygen and nitrogen levels are controlled at levels often not exceeding 20 parts per million. Excess gases can cause microvoids to form inside the monolith during cooling. Immediately after pouring the molten metal, which can exceed 2,700 degrees Fahrenheit, time becomes the most critical factor in this process. Unlike small ingots that can cool quickly, a steel giant weighing hundreds of tons cannot be cooled rapidly. If cooling happens too fast, it leads to massive internal stresses, cracks, and structural defects because the outer layer solidifies while the steel inside is still liquid. To ensure uniformity of the crystalline structure, the 607-ton ingot was left to cool in the casting pit for 6 weeks. This is a controlled, incredibly slow process, during which the steel gradually solidifies, dropping to a temperature of around 2,000 degrees. This slow crystallization allows the metal to avoid unwanted phase transformations and guarantees a high-quality macrostructure, which is the key to the strength of the future component. Only after this lengthy solidification period is complete, the steel monolith, which after shrinkage and removal of the defective top portion weighs approximately 320 tons, is carefully extracted from the ground. The extracted ingot, despite its weight, is not yet a finished blank. It has a cast, coarse structure with large crystals. To transform it into strong, homogeneous metal capable of withstanding extreme loads, forging is required. Forging 500-ton ingots demands hydraulic presses with working forces ranging from 10,000 to 20,000 tons. For example, forging the largest reactor components requires presses with a capacity of 40,000 tons. Before forging, the ingot is again carefully heated in specialized furnaces. This process can take weeks to guarantee uniform heating throughout the entire volume of metal. The forging itself is done on giant hydraulic presses capable of creating pressure in the tens of thousands of tons. The press breaks down large, brittle cast crystals. The pressure compresses the metal, eliminating microscopic voids that may have formed during casting. The metal gains a directional fibrous structure, which significantly increases its strength, toughness, and fatigue resistance. The forging process for such an ingot takes several months. It's a constant cycle of heating, pressing, rotating, and reheating. Each press stroke is a precise calculation aimed at achieving the required internal geometry and mechanical properties. The energy needed to maintain the furnace for heat treating ingots during a 2-week cycle can exceed 100,000 kilowatt hours. That's comparable to the annual electricity consumption of dozens of typical households. During heat treatment, the allowable temperature deviation in the furnace throughout the entire volume can be only 40 degrees, which requires the use of high-precision multi-zone control systems. After shaping the ingot, we move to heat treatment. This is the final, critically important stage for tuning the internal structure of the steel. A multi-ton steel monolith that's just survived months of casting and forging is like a clumsy giant whose final character hasn't formed yet. It's strong, but its internal structure is still chaotic, riddled with invisible internal stresses. The first step is normalization, or, as we call it, homogenization. The idea is simple. We basically stir the metal structure so it becomes absolutely uniform throughout the entire volume. This ensures that at every point in the workpiece, both on the surface and deep inside, the steel has identical properties. It's like evening out the temperature in an oven so your cake bakes perfectly. Then comes the most dramatic moment, quenching. The workpiece is heated to a very high temperature, bringing it to peak plasticity. And then, rapidly, but under strict control, it's cooled. This could be a water or oil bath. This shock to nature transforms the soft steel structure into something maximally hard and strong. This gives the part its core fighting strength, but there's one side effect. The metal becomes brittle as glass, and massive internal stresses appear. If you leave it in this state, it can crack from the slightest impact. That's why the final, and most humane stage is tempering. The piece is carefully reheated, but this time to a much lower temperature. The goal isn't to change the strength, but to release the internal stresses that formed during rapid quenching. This process is like taking a deep breath after stress. It increases the steel's toughness, making it resistant to impacts and loads, eliminating brittleness. Only after successfully completing this full month-and-a-half cycle of character hardening is the steel ready to become part of a reactor or a giant press. But what are these steel giants for, into which so much time and resources have been invested? They become critically important components in industries where the price of failure is unacceptably high. For example, in nuclear power, these ingots are transformed into key components of high-pressure reactors. Picture this: pressure, temperature, and radiation demand absolute reliability. And there can't be any seams or welds that might give way. You need just one thing: a solid, continuous monolith capable of withstanding extreme loads for decades. In heavy machinery, these giants become frames for the world's largest presses. These presses shape automotive frames, aircraft parts, and ship components. A frame that won't deform under thousands of tons of load has to be cast in one piece. And of course, there's power generation. Rotors for the largest steam turbines, or crankshafts for massive marine engines that drive supertankers and container ships. In these components, you need guaranteed strength against bending and secondary loads, and only steel produced through this incredibly complex process can deliver that. Every year, the world mines over 900,000 tons of rare earth metals. Without them, not a single smartphone, electric car, or wind turbine would work. But there's one place where most of them are born. Bayan-Obo, a massive quarry in the heart of China that supplies 70% of all the rare metals on the planet. Here, the earth glitters with metallic dust, and every dump truck hauls raw material for the future. But behind this shine hides a dark truth: lakes of toxic waste, and the price nature pays for technological progress. Stick around till the end, and you'll discover how dust and poison create the foundation of modern civilization. The story of Bayan-Obo started back in the 1920s, when geologists discovered a strange ore in this area, a mix of iron and minerals unknown at the time. In the 1950s, Chinese scientists realized that hidden here was a treasure trove of rare metals: neodymium, praseodymium, cerium, yttrium, and lanthanum. Since then, Bayan-Obo has become the heart of China's strategy that would eventually turn the country into the undisputed leader of the global rare earth market. Every year, About 270,000 tons of rare earth concentrate are mined here, more than all other countries combined. It all starts simply. Massive dump trucks the height of a 2-story building pull up to the edge of the quarry, where giant excavators with buckets like a dinosaur's mouth rip out chunks of monzonite ore. Each bucket can hold over 100 tons. The dust rises in columns, and it feels like the very air here is saturated with metal. But extracting the ore is just the beginning. The real value is hidden in microscopic inclusions of rare earth minerals. Their share in the rock is only a few %, so after extraction, the ore is crushed and sent to processing plants, where a complex chemical story begins. First, the ore is ground to dust, then subjected to flotation, a process where particles suspended in water are separated using reagents. Rare earth particles stick to air bubbles, rise to the top, while the rest settles to the bottom. This is just the first step, because the concentrate still contains plenty of impurities: iron, calcium, fluorine. Next comes chemical extraction, which transforms the concentrate into high-purity oxides. This is an extremely complex process. In specialized reactors, the ore is treated with acids, usually sulfuric or hydrochloric, sometimes with the addition of fluoride compounds. After this, the resulting solution is separated into fractions using organic solvents. Each element, neodymium, praseodymium, cerium, has its own chemical quirks, so the process requires dozens of sequential cycles of extraction, precipitation, filtration, and drying. It's these oxides that then go into the production of permanent magnets, the main consumer of rare earth metals. For example, one iPhone might contain less than 1/10,000th of an ounce of neodymium in the speakers and vibration motor. In a modern wind turbine, nearly 1,400 pounds of this element. And here's the wow fact. Just 1 gram of neodymium can provide a magnet for a turbine that generates electricity for roughly 1,000 homes. It sounds like an energy miracle, but it has a flip side. The problem is that chemical processing of rare earth ores is extremely toxic. Every gram of pure metal means tons of waste. In the Baotou area, near Bayunobo, real waste lakes have formed. Black, acidic bodies of water where radioactive elements, fluorides, and heavy metals accumulate. They're visible even from satellite. Even with modern cleaning technologies, chemical processes leave their mark on the environment. Local residents tell stories that, over the past decades, dust from the quarry and processing plants has changed the soil color, and grass around the area has been growing worse. However, the Chinese government is taking measures, implementing closed-loop water systems, controlling acidic runoff, and converting some facilities to new, green technologies, where instead of traditional acids, they use ionic solutions and membrane separation. All this is being done not just for environmental reasons, but also because China aims to maintain its dominance in the global rare earth metals market. Today, it accounts for 70% of global production and over 90% of finished oxide and magnet production. Other countries, the US, Australia, Vietnam, Malaysia, are trying to develop their own deposits, but they haven't come close to Chinese scales yet. Bayunobo has become more than just a quarry. It's a symbol of the technological era, where Earth transforms into smartphones and ore becomes electric wind. Right here, among mountains of metallic dust, the elements that power digital civilization are born. There's a certain irony in this. In the quest to create a green future, humanity has become dependent on one of the dirtiest industries. Magnets for electric cars and turbines, batteries, solar panels. All of this requires metals extracted from places like Bayunobo, and the greater the demand for clean energy grows, the deeper this giant wound in the earth becomes. Despite this, for China, Bayunobo is a source of national pride. Thousands of people work here, and the territory itself is equipped with modern infrastructure, conveyor systems, automated drilling rigs, chemical plants that operate almost without human involvement. On the surface, sensors are installed that track air composition, and in reservoirs, pollution levels are monitored in real time. Every dump truck descending into the quarry is part of a giant machine that supplies the world with energy, data, and sound. And when we hold a lightweight smartphone in our hands, it's worth remembering that a piece of this device, maybe even that very magnet in the speaker, was once dust in the Mongolian desert. Neodymium is one of the most famous, and at the same time most mysterious, rare earth metals. It's a silvery white, shiny, fairly soft metal that easily oxidizes in air, so it's usually stored under a layer of oil, or in an inert atmosphere. Sounds unremarkable, but this element has become the quiet engine of the modern technological revolution. Without neodymium, wind turbines, electric cars, headphones, laptops, and even rockets wouldn't work. In pure form, neodymium doesn't have the magnetic properties it's valued for. They appear when it's combined with iron and boron, forming an alloy. This is the material used to make the most powerful permanent magnets on Earth. One neodymium magnet can hold weight hundreds of times its own. In industry, it's called a supermagnet, and for good reason. It's what makes compact electric motors, miniature speakers, and highly efficient generators possible. One study indicates that between 2001 and 2021, Bayun Obo supplied about 60% of neodymium from China's total neodymium extraction. On one hand, Bayun Obo is a remote, harsh, and dusty place. On the other, it evokes an almost magnetic curiosity in those who want to see what modern civilization looks like in its raw material form. Bayun Obo today is not just a mine, but an entire complex with its own small town, a rare earth elements museum, and even a special viewing platform from which you can see the giant pit going hundreds of feet deep. The flow of tourists here is small by Chinese standards, but steady. These are mainly engineers, geology students, bloggers, eco-tourists, and those fascinated by industrial landscapes. In 2019, local authorities even declared Bayun Obo part of the Industrial Heritage of Inner Mongolia route to show how mining and processing have transformed the region. In tourist brochures, this place is called the heart of the rare earth planet. The road to the quarry leads through endless plains and low hills, where the wind almost never stops. The air carries the smell of metal, and from a distance, the quarry looks like a giant amphitheater, where Earth plays the starring role. Tourists aren't allowed close to the mining zone. It's too dangerous, but there are several safe spots from which you can take photos. The most striking moment is when quarry dump trucks slowly move at the bottom of the pit. They look like toys. The scale is so massive. Your smartphone weighs 5 pounds and holds a charge for 30 minutes. Your laptop's chained to the wall because the battery dies in 20 minutes. Electric cars don't exist. The battery would weigh more than the entire car and only go 50 miles. Cordless power tools, wireless headphones, anything portable, just impossible. All because we never figured out how to mine and refine one soft silvery metal that stores more energy per pound than any other practical battery chemistry. Without this metal, we'd still be stuck with 70s technology. Nickel-cadmium batteries that weigh 10 times more, last 10 times less, and leak toxic heavy metals. Your phone would need a brick-sized battery. Today, we're going inside a facility in Nevada, where this metal is extracted from ancient underground brine, and I'll show you what properties make it irreplaceable and what the world looks like if we have to use something else. The Albemarle lithium facility at Silver Peak, Nevada, sits in a desert valley 190 miles northwest of Las Vegas, and has been producing lithium continuously since 1966. 10,000 feet beneath the surface lies a massive geothermal brine reservoir containing dissolved lithium chloride that's been concentrating for millions of years. The facility pumps this brine and processes 6,000 tons of lithium carbonate annually. If lithium had never been discovered, all batteries would use nickel-cadmium or lead-acid chemistry. A lithium-ion battery stores 160 watt-hours per kilogram. Nickel-cadmium stores 40. lead acid just 30. To match a modern iPhone battery, you'd need 2.5 pounds of nickel cadmium instead of 2 ounces. The phone becomes a brick. Mobile computing doesn't exist. The first stage pumps geothermal brine from wells drilled 10,000 feet deep. This brine comes up at 200 degrees Fahrenheit, carrying 300 parts per million of dissolved lithium, along with sodium, potassium, and magnesium. The brine flows into massive evaporation ponds, covering thousands of acres, where the Nevada sun and desert wind do the work. Over 12 to 18 months, the water evaporates, and lithium concentration increases from 300 to 6,000 parts per million. This creates lithium's first critical property. Extreme reactivity makes it the lightest metal that can store electrical charge. Lithium atoms give up electrons more easily than any other practical metal, exactly what you need in a battery anode. Without this, you'd need heavier metals like nickel or cadmium, which means heavier batteries for the same energy. After evaporation, the concentrated brine moves to a chemical plant where it's treated with sodium carbonate to precipitate lithium carbonate as a white powder. This powder is washed, filtered, and dried to 99.5% purity. Lithium carbonate looks like fine white sand, ready to ship to battery manufacturers. Lithium's voltage characteristics become critical here. A lithium-ion cell operates at 3.7 volts. Nickel-cadmium runs at 1.2 volts. To match lithium's voltage, you'd need 3 times as many nickel-cadmium cells wired in series, tripling the weight and complexity. A 6-cell lithium laptop battery would require 18 nickel-cadmium cells. A 1-pound battery pack would weigh 7 pounds, making laptops impossible to carry. Lithium carbonate gets shipped to battery manufacturers, where it's processed into lithium metal or lithium compounds for battery cathodes and anodes. Modern lithium-ion batteries use lithium cobalt oxide or lithium iron phosphate for the cathode and graphite with embedded lithium for the anode. During charging, lithium ions move from the cathode to the anode through the electrolyte. During discharge, they move back, generating current. This reversible movement creates unmatched energy density. A lithium-ion battery handles 1,000 cycles while retaining 80% capacity. Nickel-cadmium manages 500 cycles. Lead-acid gets 300. Without lithium, devices need battery replacement twice as often, generating toxic waste because nickel-cadmium contains poisonous cadmium and lead-acid contains brain-damaging lead. Battery manufacturers shape lithium electrodes into thin sheets and stack them with separators, creating battery cells. Multiple cells connect to form packs for phones, laptops, cars, and tools. Each application demands specific energy density and safety features, but all depend on lithium's unique properties. Lithium's power-to-weight ratio is revolutionary. The Tesla Model 3 has a battery pack weighing 1,000 pounds that stores 75 kilowatt-hours, delivering 300 miles of range. With nickel-cadmium, you'd need 6,000 pounds of batteries to match that energy, but the car weighs only 3,500 pounds total. The battery weighs more than the car. You can't build a practical electric vehicle. Tesla doesn't exist. Electric cars remain a failed experiment from the early 1900s. Every batch of lithium and every battery goes through rigorous safety testing, and there's a specific reason why lithium battery safety standards are so incredibly strict. In 2016, Samsung released the Galaxy Note 7 smartphone with a lithium-ion battery that had a design flaw. The internal structure allowed the positive and negative electrodes to touch under certain conditions, creating a short circuit. Samsung had to recall 2.5 million phones globally. The recall cost them $5.3 billion. Airlines banned the Note 7 on flights. The incident nearly destroyed Samsung's phone business and proved that lithium batteries demand perfect manufacturing with zero tolerance for defects. Today, every lithium battery undergoes crush testing, puncture testing, thermal cycling between -40 and 150 degrees Fahrenheit, overcharging, and internal short-circuit simulation. The rejection rate for lithium battery cells is around 8%. Lithium that's passed all testing gets shipped to electronics manufacturers around the world. The Silver Peak facility produces 6,000 tons annually, but global production is roughly 400,000 tons because demand is massive. Without lithium, portable electronics barely exist. Your phone stays plugged into the wall, like it's the 80s. Laptops are 20-pound luggables with 30-minute battery life. Wireless earbuds, cordless drills, e-bikes, drones, portable medical devices, none of it exists. Anything portable and electronic requires a gas generator or an extension cord. Electric vehicles are impossible. Every automaker tried EVs with lead-acid or nickel metal hydride batteries in the 90s and 2000s. All failed. Maximum range 60 to 80 miles. Batteries died after 2 years. Without lithium-ion, Tesla never gets started. EVs remain a failed technology, and we're stuck with gas cars with no viable alternative. Renewable energy storage doesn't work at practical scale. Solar and wind need massive batteries to store energy when the sun doesn't shine or the wind doesn't blow. Without lithium, these systems would be warehouses full of lead-acid batteries weighing 50 times more, costing 10 times more, needing replacement every 3 years. Grid-scale energy storage is economically impossible. Renewable energy remains tiny because it's too unreliable without storage. Without this lightweight, high-voltage metal, we're stuck in a world where electronics stay plugged into outlets, portable devices don't exist, electric cars are impossible, and renewable energy can't replace fossil fuels. You've seen how brine containing 300 parts per million lithium concentrates through evaporation to 6,000 parts per million. How chemical processing creates 99.5% pure lithium carbonate. How lithium's properties create batteries with 4 times the energy density of alternatives. And why the Galaxy Note 7 proved that lithium production demands absolute precision. If this hooked you, subscribe for more content making modern life possible. Thanks for watching. Every year, machines are built around the world so massive and powerful that a single one could supply electricity to an entire city and costs as much as dozens of private jets. But what if I told you that inside this colossal structure, there are parts machined with precision, thinner than a human hair, and that one tiny mistake could cost millions of dollars or even destroy everything? Today we're going inside a place almost no one gets to see, the heart of turbine manufacturing. And trust me, what you're about to see will completely change how you think about engineering, if you stick around till the end. Let's start with the fact that there are 2 main types of these turbines, and they work on very different principles. First, the steam turbine. You'll find these at nuclear and thermal power plants, on massive tankers and icebreakers. Second, the gas turbine. It's more like a giant jet engine without wings and lives mostly at gas-fired power plants and on some military vessels. Here at the factory they make both types, but we're heading first to the steam ones because they're older, more massive, and look like they were invented 2 centuries ago. Which, actually, they were, but they're still very much around. How a steam turbine works, short and formula-free. There's a boiler that heats water into pressurized steam at anywhere from 800 to 3,000 pounds per square inch. This steam, hot, pressurized, angry, blasts through nozzles onto rotor blades. The blades start spinning. The rotor spins the shaft. The shaft spins a generator or a ship's propeller. The steam cools down, condenses back into water, and returns to the boiler. The cycle is closed. Sounds simple, but for this simple not to explode into pieces and to run for 3 years without major repairs, you need all of this around me. The first shop they take me to is the foundry. This is where every turbine begins. The casing, the outer shell that holds all the internal components under pressure, is cast from alloy steel or cast iron, depending on operating parameters. For steam turbines in large power plants, the casing is cast in 2 or 3 tiers, and each tier is a separate mold. The mass of 1/2 of a casing can reach 60 to 80 tons. The metal is melted in arc furnaces with a capacity of 50 to 150 tons of molten metal, and the temperature there is around 5,000 degrees Fahrenheit. The mold for a large casing is a pit in the floor, 6 to 10 feet deep, lined with refractory clay. The metal is poured through a system of channels, and the entire process of filling one large mold takes 15 to 30 minutes. Then the casting cools, naturally from several days to 2 weeks, depending on the mass. After cooling, the casting goes to its first inspection. Ultrasonic testing searches for voids and inclusions inside, spots where the metal didn't fuse the way it should. X-rays check critical zones. If they find something significant, the casting goes back to remelt. No compromises. The rejection rate at this stage runs 3 to 8% depending on the casting's complexity, and that's completely normal for parts this size. Next, machining. Now, here in the shop floor, there are machines that made my jaw drop. The horizontal boring mill that machines the inner casing surface. It's about 60 feet long. The table where the part sits moves. The spindle stays put. The tool freely bores the bearing and seal mounting surfaces to an accuracy of plus or minus half a thousandth of an inch. Why so precise? Because the rotor spinning inside at 1500 to 3600 revolutions per minute has a clearance between its blades and the casing of 50 to 150 microinches. 1% efficiency loss at a large power plant. That's millions of dollars in extra fuel costs per year. The rotor is the star of this story. It's a shaft carrying discs with blades, and it's the most complex part of the entire turbine. The shaft for a large steam turbine is a forging made from special chromium molybdenum vanadium steel, 20 to 40 feet long and weighing 20 to 60 tons in its rough state. A forging means you take a red-hot ingot of metal and just hammer it with a press weighing 5,000 to 50,000 tons to give it the shape you need. The grain structure of the metal during forging gets oriented along the shaft's axis. That's how you achieve torsional strength. After forging, the shaft goes through heat treatment again, then heads to the machine shop. Turning takes 2 to 4 weeks of continuous work on a lathe that's nearly 70 feet long. Chips fly, coolant flows, and machining away from that massive blank reveals the sleek shaft you saw in the drawings. This is the part where I'm always amazed. A gigantic component, yet precision like a watch mechanism. Blades are a separate production line. Steam turbines at large power plants have anywhere from 8 to 20 stages, and each stage is a disc with blades. First stage blades are small, sometimes less than 2 inches tall, because the steam there is still under high pressure and dense. Last stage blades are massive, up to 5 or 6 feet long on the largest turbines. These blades are forged and milled from iron-based alloys or stainless steel, and in their final profile, they have an aerodynamic shape with precision to within plus or minus 2/1000 of an inch along the entire length. Each blade is checked for resonant frequency. It can't match the operating rotational frequency of the rotor, or else after a few thousand hours, a fatigue crack will develop from vibration. How they test this is simple. They tap the blade with a small hammer and listen with a special acoustic sensor. A very elegant method for such a serious problem. Assembling the rotor. This is when it starts to feel like an operating room. Bladed discs get mounted onto the shaft using shrink fitting. The disc gets heated to 300 to 400 degrees Fahrenheit. It expands, slides onto the shaft, then cools and grips the shaft with a force no bolt could ever match. No threads, no glue, just temperature difference and precision sizing. The interference fit when cold, 1 to 3/1000 of an inch per inch of diameter. After assembly, the rotor gets balanced, and this takes 1 to 3 days. Balancing happens on a specialized rig, where the shaft spins on bearings while sensors register vibration. If there's any imbalance, metal gets removed from certain spots, or balancing inserts get installed. Allowable residual vibration on a large rotor, fractions of an ounce per inch of radius. If you think that's strict, you're thinking right. After assembly, the turbine heads to the test stand. At full operating parameters, pressure and temperature, they run the turbine for 24 to 72 hours. Sensors track bearing temperatures, vibration, steam leaks, power output. If anything goes outside the limits, stop, disassemble, analyze. There have been cases where they found a defect here that the X-ray missed initially. So the test stand isn't just a formality. It's the last line of defense before shipping. The finished turbine gets broken down into transport blocks, casing separate, rotor separate, auxiliary equipment separate. A large turbine rotor travels on a special trailer with hydraulic suspension, the kind you've seen on YouTube, with 18 axles moving at 20 miles per year. They coordinate the route a month in advance. Every bridge height and every turn width needs checking from the factory to the port or customer. Sometimes for one of these transports, they temporarily remove road signs and even take down power lines over the highway. I asked the chief engineer how many turbines they build per year. He said 12 to 20 of various types. That's it. Less than 2 per month. But each one runs for 30 to 50 years and generates electricity for hundreds of thousands of people every day. Some things don't need high-volume production. What if one of the most common metals on Earth has a hidden property that even some engineers still underestimate? A metal that boils like water and vanishes into thin air during production, only to be reborn as gleaming ingots. We see it every day, but almost no one knows what the underground cities where it's mined look like, or what giant machines make the ore ignite like little controlled earthquakes. In this video, you'll discover things you never suspected, and by the end, the main secret will be revealed that will forever change how you think about zinc. Zinc is the 4th most consumed metal in the world, right after iron, aluminum, and copper. That alone tells you just how critical it is for the global economy and industry. Annual worldwide zinc production runs somewhere between 12 and 13 million metric tons. We're talking massive volumes here, which really drives home how irreplaceable this metal is across hundreds of different applications. The main zinc mining regions are China, Australia, and Peru. These 3 countries together account for a huge chunk of global zinc ore production, making them the key players in the market. For instance, China isn't just the world's largest producer, it's also the biggest consumer of zinc, which reflects its massive industrial growth. Other major producers include India, the United States, Mexico, and Canada. As for reserves, the U.S. Geological Survey estimates that global zinc reserves sit at around 250 million metric tons. Beyond that, there are what we call resource bases, essentially potential deposits that haven't been fully explored yet, or aren't economically viable to mine right now. These are estimated at over 1,800,000,000 tons. These numbers tell us that zinc, unlike some rare metals, will be around for many decades to come, even with consumption on the rise. The biggest user of zinc is the galvanizing industry, which uses it to protect steel from corrosion. This sector accounts for roughly 60% of all zinc produced. This shows just how critical zinc is for construction, automotive manufacturing, infrastructure production, and countless other industries where steel's strength and durability are essential. Without zinc coating, the lifespan of steel products would drop dramatically, leading to massive economic losses and a huge spike in resource demand. 15 to 20% of zinc is used to produce alloys like brass and die casting alloys. These alloys are used in making parts for cars, household appliances, toys, plumbing fixtures, and electronics. Another 10 to 15% goes into making zinc oxide and other chemical compounds. Zinc oxide has a ton of uses, from sunscreens and cosmetics to paints, ceramics, the rubber industry, and even animal feed supplements. Its antibacterial and protective properties make it a versatile ingredient. The rest of the zinc goes into battery production, as a micronutrient in agriculture to boost crop yields, and in pharmaceuticals and dietary supplements, since zinc is essential for the human immune system. When it comes to pricing, like most commodities, zinc prices fluctuate based on global supply and demand, economic cycles, and the situation in major producing and consuming countries. However, demand for zinc remains stable or growing, driven by urbanization, infrastructure development, and the worldwide need to protect metals from corrosion. This makes zinc an important indicator of global economic health. Most zinc is extracted from underground mines. These are entire underground cities stretching hundreds of feet and sometimes several miles beneath the Earth's surface. We're not talking about simple holes in the ground. These are networks of tunnels, shafts, ventilation systems, and hoisting structures. It all starts with exploration. Geologists work like detectives, searching for what's called ore bodies, sections of rock where the concentration of zinc is high enough to make mining it profitable. Now, zinc typically shows up as a sulfide ore, like sphalerite, and it almost always comes bundled with lead, silver, and sometimes copper. Once they've located a deposit, the real work begins: building the mine itself. This involves sinking vertical shafts that serve as the main access points for getting to the ore, hauling materials up and down, and moving equipment in and out. They also create horizontal tunnels, what miners call drifts, that lead straight to the ore veins. The actual ore extraction is where things get dynamic and risky. Miners bring in specialized gear, powerful drilling rigs that bore holes into the rock face, called blast holes. These holes get packed with explosives. Then comes the carefully controlled blast that breaks apart massive volumes of rock. Think of it like a controlled earthquake on a smaller scale. Dramatic, but completely under control. The dusty air is quickly removed by powerful ventilation systems, which also bring fresh air deep underground. The blasted ore is then loaded into massive underground haul trucks or onto conveyor belts using heavy-duty loaders. It's like a non-stop underground highway, constantly moving tons of ore to the main hoisting shafts. From there, the ore is lifted to the surface using powerful elevators or specialized conveyor systems that climb hundreds of feet vertically. At every stage, from drilling to hoisting, strict safety protocols are followed because working underground demands maximum caution. Once the ore reaches the surface, it still looks like ordinary rock containing only a small percentage of zinc. To extract the valuable mineral, the ore goes through a processing plant, a whole complex of sophisticated processes. The first step is crushing and grinding. Massive chunks of ore feed into crushers that break them down into smaller pieces with a deafening roar. This crushed ore then goes into ball or rod mills, giant rotating drums filled with steel balls or rods. Inside these mills, the ore gets ground down into an extremely fine powder, almost like flour. This is critical to free the zinc mineral crystals from the surrounding rock. The next key stage is flotation. The ground ore powder gets mixed with water and special chemical reagents in large tanks called flotation cells. These reagents selectively stick to the zinc mineral particles, making them water repellent. Then air is pumped through this mixture, creating millions of tiny bubbles. Particles of zinc mineral latch onto these bubbles and float up to the surface, creating foam. Other unwanted minerals stay at the bottom. This enriched foam is collected. That's your zinc concentrate, which can pack up to 60% zinc. Since zinc often hangs out with lead, the plant might run several flotation cycles to separately pull out zinc concentrate from lead concentrate. The zinc concentrate you get, it's still not pure metal. It's got to go through metallurgical processing to turn into actual metallic zinc. And this is where we enter the world of extreme temperatures. If they're using the pyrometallurgical method, the zinc concentrate first gets roasted. The concentrate is heated in special furnaces at around 1,800 degrees Fahrenheit. This burns off the sulfur that's part of the sulfide ore, converting it into zinc oxide. During this process, the sulfur transforms into sulfur dioxide gas, which gets collected and used to produce sulfuric acid, a crucial industrial product. This not only cuts down on air pollution, but also creates an additional valuable byproduct. Next, the zinc oxide gets mixed with coal and heated to even higher temperatures, over 2,200 degrees Fahrenheit, sometimes reaching as high as 2,700 degrees, depending on the specific furnace technology. At these extreme temperatures, a reduction process takes place. The carbon strips away oxygen from the zinc oxide, releasing pure metallic zinc. And here's where that amazing evaporation effect happens. At these temperatures, the metallic zinc transitions into a gaseous state. Basically, it evaporates. Zinc has a relatively low boiling point compared to other metals. So in these furnaces, where the temperature is way higher, zinc literally turns into vapor that rises up and gets captured in special condensers. There, the vapor cools down and condenses, turning back into liquid metallic zinc. This liquid zinc is then poured into molds to create ingots or pellets. In every country, asphalt is just a road. But in Dubai, it's a challenge to nature. Here, air temperatures reach 122 degrees in the shade, while the road surface heats up to 160. Regular asphalt would melt within just a few days, but engineers found a way to make it survive. Polymers that hold their shape even at 176 degrees, geotextile membranes that breathe, and sensors that detect defects before human eyes can spot them. Why don't these roads melt like ice in the sun? And what strange technology did they test to make them actually dry after rain? Watch till the end. The finale will surprise you. Standard asphalt consists of stone aggregate and bitumen, a dark, thick substance that holds the mixture together, making it uniform and strong. However, bitumen has one weakness. It starts to soften at temperatures around 113 degrees Fahrenheit. For countries with moderate climates, this isn't a problem since road surfaces rarely reach such heating levels. But Dubai has completely different conditions. There, summer air can heat up to 122 degrees in the shade, while the road surface under direct sunlight can reach 160 degrees. Under such conditions, regular asphalt would literally behave like warm rubber. It would become soft, start deforming under vehicle weight, and in places simply slide off slopes. Plus, sharp temperature changes between scorching days and relatively cool nights would cause cracks to appear. In countries where occasional short heat waves occur, people might not immediately notice these processes. Sure, we sometimes get 104 degrees in summer, but such temperatures don't last long, and the surface deteriorates slowly, gradually. In Dubai, however, high temperature isn't just present, it's constant and stable for several months. This means asphalt is under continuous stress, and if you don't account for this factor, the road literally won't survive. That's exactly why engineers had to find a solution that would allow asphalt to maintain its shape even under extreme heating conditions. They replaced regular bitumen with modified bitumen, with polymer additives that change its physical properties. Such bitumen holds its shape at temperatures up to 176 degrees Fahrenheit. This means even when the road surface heats up to maximum levels, the material still remains stable, doesn't flow, and doesn't change structure. The difference might seem small at first glance. What's a few dozen extra degrees? But this exact difference makes Dubai's roads smooth, even, and durable, even when it's almost impossible to breathe from the heat around you. So what is this modified bitumen? The process is based on mixing bitumen with polymer additives. Polymers act like a reinforcing network at the molecular level. They stretch the bitumen structure, making it more elastic and heat-resistant. As a result, the asphalt doesn't soften. It maintains stability and shape even when heavy bus or truck wheels press on it for hours. The mixing process also isn't limited to just adding polymers. It's crucial to properly select the stone aggregate composition. Stones of different sizes create a framework-like structure, and bitumen here acts not as the main material, but rather as what connects the elements together. If the aggregate is selected incorrectly, bitumen will have to take on too much load, and even the modified mixture will lose stability. Therefore, asphalt composition is always a precise calculation of material ratios that don't just connect, but work as a unified system. But asphalt is just the surface. Hidden beneath it is a multi-layered sandwich that determines the road's durability. The first layer is sand, but regular sand won't work. It's mobile, can shift, and the road would lose its evenness within months. So sand is stabilized by mixing it with cement or special substances that make the mixture less mobile. Next comes a crushed stone layer that provides hardness and distributes load. Special geotextile fabrics can be laid between layers, preventing settling and material mixing. Geotextile works as a membrane that allows water to pass through, but doesn't let soil particles mix. This keeps the construction stable for many years. The way asphalt is actually laid also plays an important role. Work is usually done at night when temperatures are lower. This is necessary so bitumen cools evenly and gains the required hardness. If you lay asphalt during daytime heat, its surface will cool unevenly, creating stress in the structure that will eventually lead to microcracks. After laying, roads are regularly checked using special machines equipped with sensors and thermal imaging cameras. If sections are found where temperature is too high or irregularities appear, they're repaired immediately, not waiting until the problem becomes visible to drivers. Experiments with cooling coatings deserve special mention. In some districts, asphalt is painted or covered with a special compound that reflects sunlight and reduces surface heating by 10 to 15 degrees. This is important in pedestrian areas since road surface temperature affects how hot the air gets at foot level. This way, even a regular walk becomes less exhausting. In Dubai, roads aren't left unattended until large potholes appear. Control happens constantly and systematically. Special vehicles with measuring equipment travel highways and city streets, recording the smallest irregularities. Sensors read surface deviations, and computers compare them to standards. If there's suspicion of overheating or beginning deformation, the section is checked with thermal imaging cameras. High temperature indicates that bitumen is losing rigidity, and the surface might start settling. Thanks to such monitoring, repairs are done not when it's too late, but when the first changes begin. Repair work is conducted mainly at night when temperatures are lower and material cools evenly. This extends the road's service life and avoids repeated damage. The approach is based on the idea that infrastructure should work continuously, not wait for the moment when it becomes a problem for drivers. According to Dubai municipality data, after switching to polymer-modified mixtures, the number of deformation waves on roads decreased by approximately 40% during the first 2 years. Meanwhile, road surface service life increased on average from 7 to 10 years to 12 to 15 years before the first major repair. This significantly reduces overall infrastructure costs. Although initial polymer asphalt installation costs are higher by approximately 15 to 20%, long-term savings can reach 50% due to reduced repair needs. There's also data on experimental light reflective coatings being tested in residential areas and near pedestrian zones. On average, such coatings reduce road surface temperature by 10, or even all 14 degrees, depending on conditions. According to observations, in areas with cooling roads, air temperature at pedestrian foot level also drops by 2 to 3 degrees, reducing thermal load on people and making outdoor stays more comfortable. Statistics also show that, with early detection of surface microdefects, their elimination takes on average 3 to 6 hours, while if you wait for visible damage to appear, repairs can last from several days to several weeks and require closing road sections. Therefore, the city focuses on regular monitoring. In 1 month, control vehicles can cover over 80% of the city's road network. Dubai once tested asphalt that absorbs solar energy, then radiates stored heat at night to dry roads faster after rare rainfall. Turns out, the surface works like a giant thermos. During the day, it accumulates energy, and at night gradually releases it. The experiment showed such roads can dry 30% faster. And this is really needed, because after desert rain, water doesn't absorb into the ground, but can stand on asphalt for hours or even days. So the technology solves a problem that doesn't even exist in most countries. You know how this experiment ended? Your house has no electricity. Your phone doesn't exist. The internet is physically impossible. Electric motors of any kind can't be built. And human civilization is frozen in the 1800s with steam engines and gas lamps. All because we never figured out how to refine one reddish metal that conducts electricity better than anything else except silver. which costs 50 times more. Without this metal, every wire would need to be 3 times thicker and cost 4 times as much. Power grids couldn't reach beyond cities. Your electric bill would be $1,200 monthly. Today, we're going inside the factory in Utah, where this metal gets refined to 99.99% purity, and I'll show you why that purity matters, and what would happen if we used something else instead. The Kennecott Copper Refinery in Magna, Utah, sits 12 miles west of Salt Lake City, and has processed copper continuously since 1903. This facility receives ore from Bingham Canyon Mine 20 miles south, the largest man-made excavation on Earth visible from space. The refinery processes 300,000 tons of copper per year, and every step creates properties that make electrical civilization possible. Raw copper ore contains only 0.6% actual copper mixed with rock and minerals. If copper was never discovered, we'd use aluminum for electrical wiring. Aluminum conducts only 60% as well as copper, meaning you need 50% more cross-sectional area for the same current. Every wire in your house would be thicker and heavier. Building construction costs would increase 30% just from wiring. The first stage crushes ore into powder and mixes it with water and chemicals in flotation tanks. Air bubbles blow through, and copper minerals stick to bubbles and float as froth while waste rock sinks. The froth contains 30% copper, a 50-fold increase from raw ore. This concentration matters because copper's conductivity depends entirely on purity. Even tiny impurities dramatically increase resistance. 1% phosphorus increases resistance by 50%. 0.1% arsenic doubles it. Without purification, we'd use metals that lose huge amounts of energy as heat. Power companies would generate 3 times more electricity just to compensate for transmission losses, 3 times more power plants, fuel, and pollution. Concentrated ore moves to the smelter and heats to 2,200 degrees Fahrenheit. Copper melts and separates from sulfur and iron, which become slag. What emerges is blister copper at 98% purity. Better, but not good enough for electrical use. Copper's heat tolerance becomes important here. It carries high currents without melting, doesn't melt until 1,984 degrees Fahrenheit. Aluminum melts at only 1,221 degrees. In electric vehicle motors or transformers, aluminum would literally melt under load. Electric motors would need to be 3 times larger to keep current densities low enough. A 200-pound copper motor would weigh 600 pounds in aluminum and deliver less power. Blister copper moves to electrolytic refining, the most critical stage. Impure copper sheets become anodes in giant tanks with acidic copper sulfate solution. Pure copper cathodes sit opposite, and when current passes through, pure copper ions migrate to cathodes while impurities fall to the bottom. After 12 days, cathodes are coated with 99.99% pure copper. This extreme purity creates extreme conductivity. At 99.99%, copper conducts so efficiently that a mile-long wire loses only 2% power as heat. At 98% pure, that wire loses 15%. With aluminum at any purity, you lose 5 to 8%. The United States has over 600,000 miles of high-voltage transmission lines. If those were aluminum instead of copper, we'd lose 200 billion kilowatt-hours per year in transmission, enough to power 20 million homes. Your electric bill would triple. Pure copper cathodes get melted and cast into forms. Some become wire rod drawn through progressively smaller dies, creating wire from thick power cables to hair-thin magnet wire. Others get rolled into sheets for circuit boards and building materials. Each application requires different properties, but all depend on 99.99% purity. Copper's combination of conductivity and ductility becomes critical here. Copper can be drawn into micron-thick wire without breaking. Aluminum is brittle. When you bend aluminum wire repeatedly, it cracks. This is why every electric motor uses copper windings. The wire bends around tight curves hundreds of times during manufacturing without breaking. Without copper, we couldn't mass-produce electric motors. No motors means no electric vehicles, power tools, washing machines, fans, or pumps. Every copper batch goes through rigorous testing, and there's a specific reason purity standards are so strict. During the 1960s and early 70s, copper prices spiked, and builders used aluminum wiring in homes to save money. Aluminum was cheaper, but had higher resistance, running hotter under load. The real problem was connections. Aluminum expands and contracts more than copper when heating and cooling. Over months of electrical cycling, aluminum wire worked loose from connection points. Loose connections create more resistance and heat. The insulation would char and ignite. Between 1965 and 1973, tens of thousands of house fires traced back to aluminum wiring. Dozens died. Insurance companies refused to cover homes with aluminum wiring. That crisis proved copper can't be substituted. Today, every copper product goes through conductivity testing. Pure copper at 20 degrees Celsius has conductivity of 58 million Siemens per meter. Anything below 57 million gets rejected and reprocessed. They also do bend testing, thermal cycling, and microscopic inspection. The rejection rate is 6%. Copper that passes inspection ships to manufacturers making electrical wire, motors, and electronics. Kennecott produces 300,000 tons yearly, but global production is 25 million tons because demand is enormous. Without copper, no electrical grid exists as we know it. Thomas Edison tried iron wire for electrical distribution in the late 1800s. It didn't work. Resistance was so high that power couldn't travel more than a few blocks. Without copper, electrical power is limited to buildings with their own generators. No power lines between cities. Every building needs its own coal or diesel generator running constantly. The internet is physically impossible. Fiber optics carry data long distances, but electronics at each end require copper for power and short-range transmission. Data centers use thousands of miles of copper cabling. Without copper, you might have mechanical telegrams, but no electronics, computers, or digital communication. Electric motors don't exist in practical form. Every motor requires copper windings for electromagnetic fields. Aluminum motors are 3 times larger for the same power, overheat easily, and fail quickly. Without copper motors, manufacturing never industrialized beyond steam power. Modern factories don't exist. Every product is more expensive because it's made by hand. Transportation is completely different. No electric trains. You're stuck with diesel locomotives. No electric cars. Tesla doesn't exist because you'd need a 6,000-pound aluminum motor to move a 2,000-pound car. Ships use massive diesel engines instead of efficient electric systems. You've seen how copper ore concentrates from 0.6% to 30% through flotation, how 2,200 degree smelting separates copper from impurities, how electrolytic refining creates 99.99% purity, making efficient electrical transmission possible, and why the aluminum wiring crisis proved copper can't be substituted. If this interested you, subscribe for more deep dives into materials making modern life possible. Thanks for watching. Every year, over 80,000 wind turbines are installed worldwide. But few people know that each one hides a true engineering masterpiece inside. A blade over 300 feet long that can withstand hurricane-force winds and operate for decades. How do you create a structure so light it can be lifted by a crane, yet so strong it won't break even at rotational speeds exceeding 180 miles per hour? From glass and carbon fiber to vacuum resin infusion, the process of manufacturing wind turbine blades resembles precision surgery on a spacecraft scale. Stick around till the end, and you'll discover why these giant wings have become the symbol of a new energy revolution. Modern megawatt-class turbine blades range from 196 feet to 262 feet in length, and for offshore projects can exceed 360 feet. Why such size? A wind generator's power output is directly proportional to the square of blade length. A longer blade captures a larger wind area, increasing efficiency and consequently, project profitability. However, with increasing size comes a cubic increase in mass. If you simply scale up a blade, its weight becomes unacceptable, and gravitational and inertial loads become destructive. So the key challenge is maintaining low weight with colossal strength. To solve the weight problem, American manufacturers have almost completely abandoned traditional metals in favor of advanced composite materials. Fiberglass is the primary material. It's relatively cheap, strong, has excellent fatigue resistance, and provides necessary stiffness. Fiberglass cloth forms the outer shell and most of the internal structure. For the longest and most powerful blades, carbon fiber is indispensable. It's twice as light and several times stronger than fiberglass. It's strategically used in the most heavily loaded zones, in the longitudinal beams called spar caps that run the entire length of the blade and are responsible for its structural integrity. The fibers are impregnated with epoxy or polyester resins, which, when cured, bind the fibers into a single, extremely strong monolith. This is the heart of the process. To create sandwich structures that give the blade volume and stiffness at minimum weight, analogous to honeycombs, lightweight core materials are used, such as balsa wood or specialized polymer foams. Manufacturing a blade is a multi-month process that requires surgical precision, even though it takes place in massive facilities. The first step is creating a giant mold, or matrix. This typically consists of two massive halves made of durable composites or steel. The mold must perfectly replicate the complex aerodynamic profile of the future blade. Profile accuracy is critical for aerodynamic efficiency and noise minimization. Spar caps are essentially the blade's spine. At this stage, strips of carbon fiber or fiberglass are laid down. If the blade is very large, this process is often fully automated. Robotic systems precisely lay fiber layers into special grooves in the mold. This part is the thickest and bears the main bending loads. The next step is laying fiberglass layers that form the blade's outer shell, as well as core material blocks. Fibers are typically laid by hand by experienced technicians, or using automated fiber placement to ensure proper fiber orientation that will resist predicted loads. After laying all the dry layers, the mold is closed and a deep vacuum is created inside. Resin, epoxy, or polyester is introduced into the mold, and vacuum pressure uniformly and completely impregnates all the fibers, displacing air and ensuring maximum density and strength. This process allows manufacturing large, nearly void-free structures with precisely controlled fiber-to-resin ratios. The resin-filled blade is placed in special ovens or left in the mold under climate-controlled conditions. Heat initiates the polymerization process, during which liquid resin transforms into a solid, strong polymer. This process is lengthy and requires constant temperature control along the entire blade length to avoid internal stresses. After curing, the blades are removed from the mold. The two blade halves, upper and lower, are joined together using special adhesive and additional composite layers. This is one of the most complex stages as it requires perfect alignment over dozens of feet. The root section is where the blade attaches to the turbine nacelle. Powerful steel or composite bushings are embedded here that will withstand enormous loads during rotation and transmit torque. After assembly, the blade is sanded and then coated with special protective coatings. These coatings, particularly on the leading edge, are vital for protecting composite material from erosion caused by rain, hail, dust, and insects, which act like sandblasting at high blade tip speeds. American manufacturers like GE Renewable Energy and TPI Composites pay special attention to quality and innovation to guarantee blade reliability for 20 or even 25 years of operation. No blade leaves the factory without thorough inspection. Since internal defects like air pockets or poor resin impregnation can lead to catastrophic failure. Ultrasonic scanning detects internal defects, voids, and composite delamination. Thermography measures thermal signatures to identify areas with varying density, such as defective bonding. Each new blade model undergoes extreme testing in specialized laboratories. The blade is bent to its strength limit, simulating the strongest wind loads and loads from its own weight to ensure it won't break. Then the blade is forcibly bent forward and backward, up and down millions of times, simulating decades of operation to test material fatigue resistance. After manufacturing comes another engineering challenge: logistics. Transporting a blade over 260 feet from the factory, often located in interior US states, to the installation site requires special low-bed semi-trailers that can rotate the blade around corners and lift it to avoid collisions with infrastructure. It's a unique logistical dance that often requires temporary road closures. Transporting blades is a logistical nightmare. Blade length can easily exceed the wingspan of a Boeing 747. To transport such structures on US roads, special extended semi-trailers are used that can lift, rotate, and tilt the blade at intersections and in mountains. This requires temporary road closures, removal of road signs, and even traffic lights. The US continues investing in developing even longer, lighter, and stronger blades, researching thermoplastic materials for better recyclability, and segmented designs to simplify logistics. This ensures that the engineering marvel born in factories will remain a key element in achieving energy security and sustainability. Some blades, especially older ones that have already served their term, instead of being recycled, are buried in specialized landfills in sparsely populated states like Wyoming. Due to their volume and composite material, fiberglass that doesn't decompose, they can occupy significant areas, becoming museums of green energy. The tips of the longest blades can reach rotational speeds of 180 miles per hour. Though they don't exceed the speed of sound, this requires the blade tip to be perfectly designed and protected from erosion. An ordinary raindrop hitting the blade at such speed has destructive force similar to sandblasting. This forces manufacturers to develop high-tech but expensive protective coatings for blade leading edges. Engineers in the US are developing smart blades that can change their shape or have segmented tips. This allows the turbine to adapt to changing wind speeds and thus increase efficiency and reduce loads. Every year, the world builds hundreds of miles of underground tunnels, but almost nobody thinks about what's holding them up above our heads. Picture this: thousands of concrete segments, each weighing several tons, assembled with precision down to the millimeter, forming tunnels where trains blast through at dozens of miles per hour. Now here's the big question: what happens if even one of them is made wrong? Today, we're diving into the place where the backbone of the subway is born, where one tiny mistake can cost millions or more. But there's a detail they usually don't show. Stick around till the end, and you'll find out what's actually hidden inside these concrete rings. Let's start with what a tunnel lining segment is, and why we need it. When a tunnel boring machine grinds its way through soil, you've got to shore up the tunnel walls right behind it, because soil isn't rock and won't hold itself up. The shield pushes forward, and behind it, installers assemble a ring from several segments, usually 5 to 8 pieces plus one keystone. The assembled ring is what you see when you're riding the subway and looking out the window. Uniform concrete sections with bolted connections along the seams. Looks mundane. Actually, an engineering solution refined over more than 150 years. The plant I visited manufactures tunnel segments for the city subway. Tunnel diameter, 21 feet. Each ring consists of 6 segments and 1 keystone. Width of one ring along the tunnel axis, 5 feet. Concrete wall thickness, 18 inches. One segment weighs close to 4,500 pounds. Monthly, the plant ships out about 600 rings, meaning over 4,000 segments. The math comes out monumental. It all starts with rebar cages. This is the exact moment when steel rods transform into a 3-dimensional structure that'll end up inside concrete and keep it from cracking under load. The rods get cut and bent on automated lines. The machine receives a program, selects the right wire diameter, bends it at the specified angle, and cuts it to size. The thinnest rods here are about 1/4 inch in diameter, the thickest around 1 inch. Then the cages are assembled by hand or welding. It's tedious and monotonous, And workers here are clearly grateful when automation handles the whole process. The finished cage gets placed into a steel mold. The mold is probably the most expensive thing in these entire factories after the presses themselves. It's manufactured for a specific project and specific tunnel diameter. One mold costs anywhere from $200,000 to $400,000, depending on the complexity of the geometry, and it's rated for several thousand cycles. Before each pour, the mold gets cleaned of leftovers from the previous cycle and coated with special release compound. Without it, concrete bonds to the steel permanently, and you can't pull the segment out without damage. The lubing process is its own science. Too much creates pores on the concrete surface, too little ruins the mold and wrecks the piece. Seems minor, but at the plant, they train people separately just for this. Next, concrete. They don't pour regular batch plant mix here. Segments get made from special grade concrete with precisely dialed in water cement ratios, aggregate size, and additives. Compressive strength, not less than 6,000 pounds per square inch. For comparison, concrete in typical residential construction runs around 3,000. This stuff is twice as dense and heavy. Additives in the mix ensure waterproofing, because subway tunnels run below the water table, and the concrete has to hold water back completely, not soak it up like a sponge. The mix is prepared in an automated plant right at the factory and delivered to the form by transport conveyor or buckets. They don't pour the entire form at once. They do it in layers with vibration in between. Vibrators plunge into the concrete, and when switched on, the vibrator squeezes out air bubbles from the mix. If you leave air in, the concrete will have voids, and porous concrete lets water through and is less strong. One segment takes anywhere from 45 minutes to an hour, accounting for all the layers and vibration. Rushing here is harmful. This is one of those cases where slower actually means better. The filled form heads into a heat treatment chamber. Steam curing, that's what it's called. The temperature inside, around 100 degrees Fahrenheit, humidity high. The goal, speed up cement hydration and let the concrete gain sufficient initial strength in 8 to 10 hours, instead of the standard 28 days. After curing, the concrete has about 70% of its design strength, enough to remove the formwork without risk of damaging the product. Demolding, the moment I hold my breath a little every time. The crane operator lifts the top part of the mold, then the side panels swing away, and the segment stands on its own. A concrete arc that was just a sloppy mix 8 hours ago. Looks solid. No wonder. 14,000 pounds of solid concrete with rebar in the center. Next, the segment gets moved by crane to a curing rack, where it'll sit for another 7 to 14 days, until it reaches full design strength. Quality control runs parallel to all this. And it's serious here, because tunnel segments aren't paving stones. Each piece gets marked and assigned a unique identification number. During the pour, they pull test cubes, small concrete cubes measuring 4 by 4 inches, that later get crushed in a press to measure the actual strength of the batch. At the same time, ultrasonic testing of finished segments. The ultrasonic device presses against the surface and measures the speed of the wave passing through the concrete. Dense, uniform concrete gives one reading, concrete with hidden cracks or voids, another. The difference shows up immediately, and that segment gets rejected. Another type of control is geometric. Each segment gets placed on a measurement stand, and all key dimensions get checked. Arc length, thickness, bolt hole positions, surface flatness. Bolt hole tolerance can't exceed 1/32 of an inch. Segments that fall outside tolerances, and it happens more often than manufacturers are willing to admit publicly, either get sent back for rework or scrapped. On large projects, the rejection rate can run anywhere from 1 to 3% of total output. Doesn't sound like much at first, but when a single segment runs $4,000 to $6,000, it adds up fast. A separate curiosity, the waterproofing profile. Around the perimeter of each segment, there's a special groove. A rubber gasket fits in there. When the segments get compressed by bolts into a ring, the rubber deforms and hermetically seals the joint. This rubber profile looks like an ordinary black strip, gets manufactured from a highly specific compound based on chloroprene rubber, withstands pressure up to 120 pounds per square inch, and lasts as long as the tunnel itself, meaning it's designed for a minimum of 100 years. Rubber that'll outlive you and me both. Bit philosophical. Shipping from the factory isn't exactly simple either. The segments are heavy, fragile around the edges, and demand careful handling. They're loaded onto specialized frames, secured with tie-downs, and a flatbed truck hauls them to the construction site. There are limits on stacking height, no more than 3 tiers, because the bottom segments can't take excessive weight from above. At the construction site, they dig a vertical shaft. The segments get lowered underground and assembled into rings right behind the shield as it pushes forward. The shield advances 5 feet, the width of one ring, and the crew installs the next one. This rhythm never stops, day or night. I step out of the plant and stop beside a stack of finished segments. Gray, slightly rough, smelling of cement. Totally unremarkable. In a few weeks, they'll be 50 feet below city streets, just sitting there. As long as the city stands. No days off, no maintenance, no attention whatsoever from the people above them. That's the fate of a concrete arc weighing 4,000 pounds. I'd complain, but the concrete doesn't seem to mind. See you on the next tour. Today, I dragged you to a place where the transparent skeleton of our cities is born. Have you ever wondered how an ordinary pile of sand transforms into massive glass panels that hold back the wind on the 100th floor somewhere in downtown Chicago or New York? It's a genuinely cool story about how we learn to tame fire and sand to make things that look fragile but can actually withstand the impact of a small truck. We're at a super-strength glass manufacturing plant, and there's real industrial energy all around us here. Forget about that brittle glass that shatters from an accidental breath. Today we're talking about a material that's the foundation of modern architecture and safety. It all starts with something really simple that you see under your feet at the beach, but with one critical caveat. The main ingredient is quartz sand. But this isn't the sand you wiggle your toes in on vacation. Here it goes through such intensive purification that it becomes purer than your thoughts on the first day after payday. Besides sand, they add soda ash and limestone into this massive steel mixer. Soda ash is needed, so the sand starts melting at a lower temperature, while limestone makes the finished glass resistant to water and chemicals. If we used sand alone, we'd need the energy of a small sun to melt it. But this way, we cheat a little. They also throw in cullet, old chunks of glass that have already served their purpose. This saves a ton of energy and money, because melting an existing structure is way easier than turning stone into liquid from scratch. This entire mix weighs hundreds of thousands of pounds and gets poured into gigantic concrete bunkers, where the big journey begins. Now we're approaching the hottest point of our journey, the furnace. This is a massive structure as tall as a 3-story building that runs non-stop for years. If you shut this furnace down even once, it would simply destroy itself, because the molten mass inside would solidify and tear the walls apart. Inside, it's a real inferno. 2,900 degrees Fahrenheit. It's so hot that if you stood nearby without special mirrored protection, your eyebrows would vanish in a second. Natural gas roars in the burners, creating an incredible noise that vibrates your bones. The mixture of ingredients slowly transforms into a viscous, fiery liquid that looks like super hot honey or lava from a volcano. This liquid slowly flows through a refractory channel to the next stage, one that forever changed the entire industry. This is a bath of tin. That's right, glass literally floats on the surface of molten metal. This process is called the float method. Tin is way denser than glass, so the glass mass spreads across it in a perfect mirror-smooth layer. Just look at this pool 160 feet long, filled with liquid tin. Glass comes out of the furnace and settles onto this metal, becoming perfectly flat through simple gravity. No grinding wheels or expensive polishing. Physics does all the work for us. This is where engineers set the thickness of your future window. Pull the glass faster using special rollers, and it becomes as thin as 1/8 of an inch. Slow it down, and you can get a solid panel a full inch thick that's not so easy to damage. Temperature here gradually drops to 1100 degrees Fahrenheit, and the glass starts to harden, transforming from fiery liquid into an endless ribbon. Next, this ribbon enters an annealing tunnel that engineers call a layer. This is where a critically important process happens. If the glass cools too quickly, internal stresses build up, and it'll literally explode from the slightest touch once it hits the warehouse. So we slowly drop the temperature over several hundred feet of travel. This demands incredible precision, because every single degree matters for the molecular structure. The glass rolls on special steel rollers that have to be perfectly smooth, so they won't leave a single microscopic scratch on the surface, which hasn't fully solidified yet and remains vulnerable. When the glass finally cools down, lasers start checking it. It's basically digital quality control, where machines hunt for microscopic air bubbles or tiny dust particles that might have snuck into the mix back in the furnace. If the system spots even the tiniest flaw, it instantly marks that spot with special paint, and automated cutters just remove the damaged section, sending it back for remelting. The cutters themselves work at incredible speeds. Sharp diamond rollers score perfect lines. Then mechanical arms confidently snap off sheets in the exact sizes needed. But this is just regular glass, the stuff you see in old buildings. We came here for the super strong material that holds up the weight of a skyscraper. To turn glass into a true iron warrior, you've got to temper it. This is my favorite stage, because it's like putting glass through brutal boot camp. A sheet of glass gets heated again to 1200 degrees Fahrenheit, then suddenly blasted with powerful jets of cold air from both sides. This thermal shock creates massive pressure on the glass surface, compressing it, while the center stays in a tensile state. This makes the glass 5 times stronger than regular glass. If you try to hit this stuff with a heavy hammer, it might just bounce right back into your forehead. And here's the best part. When this glass finally does break under incredible pressure, it doesn't shatter into sharp daggers that can slice you up. Instead, it crumbles into thousands of tiny blunt pieces. It's a global safety standard that allows us to use it in modern cars, sports arenas, and massive shopping malls. But if we're talking about skyscrapers in cities that get hurricanes, tempering alone won't cut it. That's when we use lamination. We take 2 separate sheets of glass and glue them together using a special film made of transparent polymer. This technological sandwich gets sent to an autoclave, a massive oven under pressure, where all the air gets sucked out and the film becomes completely transparent, bonding the sheets together at the molecular level. If a brick or even something heavier hits that glass, it'll spiderweb with cracks but stay hanging on that film, without creating a hole all the way through. This is the exact glass that protects people in banks or on observation decks 1,000 feet above the ground. You're standing on a transparent floor, on the 100th story, and you know for certain that polymer layer will hold the weight of 10 people without breaking a sweat. At the end of the line, we see finished steel giants being loaded onto specialized trucks. One of these sheets can weigh over 3,000 pounds, which is why people stopped using their own hands to move them a long time ago. Instead, there are powerful vacuum suction cups on cranes that grip the glass with a death grip. It's a spectacle that makes your heart beat faster. A massive, seemingly fragile panel gliding smoothly through the air, destined to become part of a new architectural structure in just a few days. The entire journey from a pile of sand to this moment took only a few hours of intense work, but packed into those hours are decades of complex scientific research and billions of dollars of investment in technology. When you see skyscrapers glistening in the sun, remember, this isn't just architecture. This is frozen fire. Molten metal and sand that went through temperatures of 5,000 degrees Fahrenheit to become transparent. Glass panels withstand wind pressure of hundreds of pounds per square foot. They don't fear snow, hail, or scorching sun. This is the material of the future, getting stronger and smarter every single year. Maybe soon we'll be building entire cities from it. Cities that are completely transparent, yet tougher than the concrete boxes of the last century. Can metal burn brighter than the sun? Sounds impossible. But one element does this every day, and we're about to touch its mystery right now. Imagine a material lighter than plastic, yet capable of withstanding loads that break steel. A material hidden in seawater, in stone, in the technology around us, but the way it's extracted looks more like alchemy than industry. And here's the thing. By the end of this video, you'll learn about a property of magnesium that even many engineers have never heard of. Ready to discover what giant furnaces, seawater, and 1,000-degree flames have been hiding? Magnesium is often called the metal that defies intuition. It's lighter than many types of plastic, weighing approximately 0.063 pounds per cubic inch, 1.5 times lighter than aluminum, and nearly 4 times lighter than steel. In your hands, it feels almost hollow inside, yet this metal demonstrates remarkable strength in alloys and can withstand loads its mass simply doesn't suggest. What's most striking is how it burns. Given sufficient temperature, magnesium produces light so intense that its brightness reaches close to 3,500 degrees Fahrenheit, and watching the flame without protection is impossible. That's precisely why magnesium flashes were once used in photography and pyrotechnics. During combustion, it forms white smoke of magnesium oxide, and the flame itself looks as if someone turned on a concentrated beam of sunlight. In nature, pure magnesium doesn't exist. It's bound up in minerals, and the two main sources are dolomite and seawater. Global estimates suggest that the oceans contain over 1.3 quadrillion tons of magnesium, making it one of the most abundant metals in a form accessible to humanity. However, extracting it from water is a complex and energy-intensive process. Picture an industrial facility on the coast where the sea is essentially raw material. Everything runs continuously through a system of powerful pumps. Pipelines stretch from the shore to the processing units, moving thousands of gallons per hour. The water flows into large open or enclosed basins resembling giant reservoirs, where it's filtered for the first time to remove debris, sand, and biological contaminants. After that, in similar tanks, a calcium hydroxide slurry is added. This happens through automated dispensers that feed the material into the water, so the reaction proceeds evenly. From the outside, it looks like a slow transformation of transparent seawater into a cloudy liquid, as if someone added fine white powder that gradually binds the dissolved magnesium into flakes of sediment. While the reaction continues, large mixers move through the pool, sometimes resembling windmill blades, only turned horizontally. They stir the liquid almost silently, so the sediment forms everywhere rather than clumping together in one spot. When the particles become heavier and start settling to the bottom, the liquid is pumped into the next settling tank. There it sits for several hours, and the solid fraction slowly settles, forming a dense layer that looks like wet cement. The upper part of the water is drained back into the sea or directed for retreatment, while the sediment is collected by special grabs or vacuum systems. Then, the sediment is rinsed with fresh water and dried in powerful drying ovens that blow hot air at speeds capable of removing an entire layer of moisture in a minute. When the mass becomes brittle, it's moved to roasting furnaces. Inside, temperatures exceed 1,380 degrees Fahrenheit, and the material gradually transforms into magnesium oxide. From the outside, it looks like an endless white ribbon of powder, being fed by conveyor into the scorching chambers and emerging with a completely different structure. The final stage is electrolysis. The oxide enters sealed high-temperature chambers where it's mixed with salt flux. This happens either in smelting vats or in special crucibles, where the material gradually transforms into a thick, molten mass. The metal chamber walls glow red from the heat, and inside, the molten material looks like incredibly thick, scorching soup. At this point, electric current passes through it. You can only watch through protective windows, because everything inside appears to glow. Magnesium begins separating into tiny droplets that rise to the surface, since their density is lower than the molten mixture. It's collected using special ladles or drainage systems, and eventually the metal accumulates as shiny silver ingots, ready for further purification or casting into molds. In the case of dolomite, everything starts at the quarry, where the rock lies in massive layers. Extraction doesn't look like romantic stone chipping. It's the work of giant excavators, drilling machines, and blasting equipment. First, the rock gets crushed right on site. Massive jaw crushers chew through refrigerator-sized chunks and turn them into material that can move along conveyor belts. From there, the dolomite heads to factory hoppers, where machines precisely meter the flow and feed it into calcination kilns. The kilns work like giant tubes heated to 1650 degrees. Inside, the dolomite slowly descends, while hot air, fed from below, passes through the entire layer of material. From the outside, you only see bright bands of glowing metal, but inside, something crucial happens. The dolomite breaks down into magnesium oxide and calcium oxide. After leaving the kiln, the hot mass travels along metal chutes and cools under powerful blasts of air. Next comes the stage where dolomite transforms into something resembling factory architecture. A tall tower with vessels, pipes, and tanks. Coke, or ferrosilicon, is fed into this tower, along with pre-crushed calcined dolomite. This mixing happens in specialized reactors that look like enormous drums, slowly rotating to ensure uniform contact between reagents. Everything appears as a continuous flow of dry, grayish powder sliding into the reduction furnace. Inside the furnace, the temperature climbs even higher, over 2,550 degrees. The heat inside is so intense that everything around glows with a dim red light. Under these conditions, magnesium oxide reacts with the reducing agent, and the metal transitions into vapor phase. This is one of the most distinctive features of magnesium production. The metal evaporates and rises through the furnace, while gaseous particles move into the condensation chamber. The chamber looks like a vertical steel cylinder, with cooled walls from the outside. Inside, magnesium vapors meet the cold surface, and the metal condenses as a shiny coating that resembles silvery frost. This coating gets periodically scraped off by mechanical scrapers or robotic manipulators operating in an environment with minimal oxygen access. The collected metal goes into protected containers, where it's melted again to remove residual impurities. The melting crucibles look like deep wells filled with glowing silvery molten metal, and extraction systems constantly work above them, protecting the metal from contact with air. The process ends with casting into molds, where magnesium cools and transforms into ingots. Each ingot represents the end of a long journey, from stone extracted by explosions to metal that emerged through evaporation and condensation. Global magnesium production holds steady at around 1 million tons per year. China supplies roughly 85% of that volume, while the United States, Israel, and Kazakhstan handle the rest. Interest in the metal grows annually because the aerospace, automotive, and electronics industries are hunting for the lightest materials possible. For example, using magnesium alloys in transportation cuts component weight by 20 to 35% compared to aluminum. That reduces fuel consumption and boosts overall efficiency. In electronics, magnesium shows up in laptop casings, camera bodies, and smartphones. It's not just light, it also absorbs vibrations well and dissipates heat effectively. In the United States, the share of magnesium in automotive parts has climbed from 3 pounds per vehicle 20 years ago to over 12 pounds in current models, and that figure keeps rising. Despite magnesium being lightweight, flammable, and extremely reactive, it's incredibly difficult to replace. It has a rare combination of mass, strength, and reactive properties that make it one of the most important structural metals of our time. And even though humanity has been producing it for only a century, the potential for its use hasn't come close to being exhausted. If current trends in aviation and electric vehicles continue, analysts predict global demand will reach 2 million tons within a decade. Every year, the world builds massive icebreakers and liners that weigh as much as entire neighborhoods. But did you know their heart no longer beats inside the hull? Engineers took an insane step. They ripped out a 30,000 horsepower engine, capable of powering a city of 25,000 people, and dropped it straight to the ocean floor in a steel capsule weighing as much as 2 Boeing 747s. This is an incredibly complex mechanism, where a rotor misalignment of a fraction of a millimeter can tear metal to shreds. Watch this video to the end, and you'll discover the shipbuilder's biggest secret. What fatal assembly mistake they hide underwater forever, and how an invisible enemy can destroy this beast in just a couple of days. From the outside, it looks like a massive metal tail bolted to the bottom of a ship. But inside, a full-fledged electric motor. They don't install it in the ship's hull, like they've done for decades. Here it's the opposite. The motor is immediately submerged in water, hermetically sealed in a steel casing, and made to work right there in the ocean. That's why this design is treated almost like an underwater vehicle. The idea to move the engine outside the ship's hull appeared relatively recently, although engineers themselves had been thinking about it for decades. Back in the mid-20th century, shipbuilders tried to get rid of long shafts, gearboxes, and complex mechanical transmissions that took up enormous space inside the vessel and lost part of the power. The real breakthrough came in the late 1980s, when Finnish engineers working on icebreakers for northern seas proposed a radical solution: relocate the electric motor directly into a rotating pod beneath the hull. The concept was developed by specialists at a shipbuilding company searching for a way to make vessels more maneuverable in ice. The first experiments looked risky. The motor needed to be completely isolated from seawater and made to run for years without maintenance. In 1890, the first working units appeared, and within just a few years, the technology started being installed on actual icebreakers. When it became clear that the rotating thruster allowed ships to move in practically any direction, cruise liner builders quickly adopted the system. Since then, this design has gradually changed the idea of where exactly a ship's heart should be located. Not inside it, but directly beneath it. From the outside, it looks like a massive metal tail bolted to the ship's hull. But inside is a full-fledged electric motor. It's not placed in the ship's body, the way it had been done for decades. Here it's the opposite. The motor is immediately lowered into the water, sealed hermetically in a steel casing, and made to operate right there in the ocean. That's why this structure is treated almost like a submarine vessel. I walk past sections of the hull that, just a few hours ago, were separate steel plates, each one several inches thick and weighing thousands of pounds. These are curved metal sheets several inches thick, already pre-rolled, so the future capsule will have a smooth, streamlined shape. Cranes slowly lift these elements and bring them together, like assembling an underwater projectile. Between the parts, they leave a narrow gap where the weld goes. During welding, sparks fly everywhere, and the metal glows orange. Workers move slowly, going over every foot of the joint several times. First, the inner seam is formed, then the outer one, after which the surface is ground down so no protrusions remain that would create water resistance. When the hull closes up, it already looks like a smooth steel torpedo. After that, inspection begins. The seams are examined with ultrasound and X-rays, searching for even the tiniest pores inside the metal. Any suspicious section gets cut out and welded fresh. Then the capsule is sealed and pressurized to levels way beyond what it'll face underwater. If there's a weak spot anywhere, it'll show up right away. Only after that is the hull cleared to handle years of work in cold seawater and constant ice impacts. Once the steel capsule is fully welded and pressure tested, they need to install the electric motor, the main power source for the future vessel. And that's when you realize just how massive everything is in marine engineering. Before installation, the motor sits on a special platform and looks more like part of a power plant than ship machinery. Its diameter is nearly 10 feet, and it weighs so much that regular lifting equipment isn't even considered. Only heavy overhead cranes do the job. The rotor, the rotating part of the engine, gets lifted separately. This massive metal ring with copper conductors weighs more than a fully loaded truck. The crane starts moving so slowly, it's almost invisible to the eye. The operator works off signals from several engineers standing on different sides of the housing, constantly monitoring the component's position. There's no room for sudden movements here. Even a fraction of an inch displacement could mean misalignment that'll show up during operation as severe vibrations. They literally lower it inch by inch, constantly measuring clearances with laser instruments. Bearings and support elements are already installed inside the housing, and all of them have to align within thousandths of an inch. If the engine shaft doesn't line up perfectly with the geometric center of the capsule, rotation will create an imbalance. After the rotor's been set, engineers won't let that crane move for a long time. A whole series of checks begins. They measure alignment, hand rotate the shaft several times, listen for the sound of metal contact. Sometimes they lift the engine again and adjust its position, spending hours on just a few millimeters of shift. Everyone here understands that once the casing closes, there's no getting back inside, so perfect precision matters more than speed. When the engine finally settles into place, the whole assembly suddenly looks complete. An empty steel shell transforms into a real powerhouse. This is the moment you could call the birth of a system that will soon spin a propeller, turn a multi-thousand-ton vessel, and run for years underwater, where no human will ever see it again. And so more people can see my channel, please subscribe and comment on the video. Modern installations can pump out up to 22 megawatts of energy. That's equivalent to over 30,000 horsepower. For perspective, one of these engines could power a small town of 25,000 people. A fully assembled installation, engine and propeller combined, can weigh over 320 tons, or more than 700,000 pounds. That's the weight of 2 Boeing 747s. The propeller attached to this pod often measures over 22 feet in diameter. Each blade on that propeller weighs as much as a full-grown elephant. Once the engine is securely tucked inside its steel casing, the moment of truth arrives, mounting the propeller. If the pod itself is the muscle, the propeller is the hand pushing against the water. And here we circle back to those head-spinning scales. Each blade is forged from a special alloy of bronze, aluminum, and nickel. This metal has to be strong enough not to bend under thousands of tons of water pressure, yet smooth enough not to create unnecessary turbulence. The blades arrive at the capsule on special pallets, each one wrapped in protective film like a piece of jewelry. Installation is done using hydraulic pushers. The propeller is mounted onto the motor shaft protruding from the capsule, and here precision is once again measured in thousandths of an inch. Any misalignment will cause the propeller to vibrate at high speed, and that vibration will simply destroy the engine bearings in a matter of days. When the propeller finally seats into place, it's secured with a massive nut tightened with a force that's hard to even imagine. After that, a streamlined cap is installed on the propeller hub. This ensures the water flow past the propeller stays perfectly smooth. The entire assembly is then coated with a special paint that prevents marine organisms and barnacles from attaching. Because even a few inches of buildup on the blades can reduce engine efficiency by 5 to 7%, which translates to losses of hundreds of thousands of dollars per year. Every nuclear reactor on the planet has an emergency brake. Not a button, not a switch. A metal. Drop it into the core, and the chain reaction stops cold. Pull it out too slowly, and you get Chernobyl. The entire world produces just 70 tons of this metal per year. That's one railroad car. One single car, standing between controlled fission and catastrophe. 5 factories make it. Maybe 6, if you count one in China that nobody talks about openly. Fewer factories than NFL teams. And here's the thing, this same metal is sitting inside your phone right now. Billions of devices, atoms-thin layers. The metal is called hafnium, and nobody told you about it. But before hafnium ends up in a reactor or a chip, it has to be ripped from its chemical twin. That separation is one of the hardest jobs in metallurgy. Hafnium never shows up alone. Nowhere on Earth. Never has. It hides inside zirconium. Every sample of zircon mineral ever pulled from the ground has 1 to 3% hafnium baked into it. Always. No exceptions. Now pay attention to this. Zirconium and hafnium are chemical twins. Same atom size. Same valence. Same behavior in almost every reaction you throw at them. So alike that Mendeleev never spotted hafnium when he built the periodic table. It stayed hidden for over 50 years, until 1922, riding on zirconium's back like a stowaway. Think about that. An element hiding in plain sight for half a century. Separating these two costs a fortune. Not because the chemistry is exotic, because the difference between them is almost nothing. So why bother? One property. One single property where they're total opposites. And that property keeps nuclear reactors from melting down. Zirconium is transparent to neutrons. They fly straight through it like light through glass. That's why nuclear fuel rods are wrapped in zirconium. Hafnium does the exact opposite. It swallows neutrons, 600 times more than zirconium. 600. That makes hafnium the emergency brake of every nuclear reactor. Control rods, the metal plates that slide into the core to kill the chain reaction, made from hafnium. When something goes wrong, hafnium rods drop in. They absorb every neutron in their path. Reaction over. American nuclear submarines run on hafnium control rods. Compact, reliable, no second chances needed. Now here's where the money starts burning. To make nuclear-grade zirconium, every trace of hafnium must come out. To get pure hafnium, it has to be stripped from the zirconium completely. Both processes happen at the same plant. Both are brutal. Both start with sand. A specific mineral pulled from beaches in Australia and Africa. What happens next involves 100 repetitions of the same chemical trick and a column of machines taller than a 3-story building. Raw material, zircon sand. Looks ordinary. Slightly heavier than beach sand. Faint metallic shimmer. It gets processed into zirconium chloride, a powder that acts like salt with an attitude. Sucks